You please kindly confirm audio video on screen. Kindly confirm audio video on screen notes. Good evening. Good evening to one and all. Yeah, good. Okay, till yesterday we have discussed about the steady state stability analysis of system. So now we are going to start the transient stability analysis. Transient stability analysis. Yeah. First of all, what is the definition for the transient stability? Transient stability analysis is the heading. Analysis. Already we discussed about the definition of stability, right? Stability means it is the capability of synchronous machine to be remains in synchronism, right? To be remains in synchronism with respect to external connected network, even after experiencing a physical disturbance. But now, in case of transient stability, what we are going to say is simply it is a capability of synchronous machine. Is the capability of synchronous machine. Synchronous machine to be remains in synchronism. To be remains in synchronism with respect to external connected network, external connected network, or you can say infinite bus bar, or you can say infinite bus bar, even after experiencing large physical disturbance. Large physical disturbance. So this is the definition of the transient stability of the system, right? Fine. Next, see, as we said earlier, because of this large disturbance, what we are seeing, because of the large disturbance, obviously omega variation with respect to time is very high. So obviously delta variation with respect to time is very high. And we said that delta versus time must be studied here. See, if you want to recall the previous steady state stability analysis we studied, we didn't think about the delta versus time there. We didn't thought about the delta versus time earlier. What we said simply is, at the initial operating condition or at the point where you are standing, if dp by d delta value was positive, if dp by d delta is positive, then simply the system will be stable for the small disturbances what you are going to give. But that type of statement we can't say for the transient stability analysis now. Okay, because delta variation with respect to time is very, very high. Right. So delta versus time must be studied here. Must be studied to say whether the system is stable or unstable, right? And for that purpose, we have to go with the rotor mechanical equations. Rotor mechanical equations. Now we are going to take up the heading like rotor mechanical equations. Else we are going to call it as swing equation. Swing equation of the rotor body. And here we have two types of machines. One is a synchronous generator, other one is a synchronous motor. So I'll take up synchronous generator swing equation first. Then we'll go for synchronous motor swing equation. Okay, yeah. So let's take swing equation for synchronous generator. Synchronous generator. Swing equation for the synchronous generator. Done. Okay. So first, as a block, I will show simply. This is the rotor of the synchronous generator. I'm showing here. of the synchronous generator. Rotor body of synchronous generator. And we have some shaft connected to this one. I will show that shaft also is one shaft connected to this, right? And we have some prime mover. Prime mover means mechanical input, we can say here, like this. It was a mechanical input. And we are going to get some electrical output from the stator. We are going to get some electrical output from the stator. I'll show simply like this. We are getting some electrical output like this. And we have some mechanical input as PS. Mechanical input as PS. Okay, next thing. Listen, please. Listen. Because of this mechanical input given to the rotor body, definitely this rotor body will experience some torque and it will rotate in certain direction with some speed. Okay, so I will show that thing. So this is the direction of the prime mover torque or mechanical torque. That's the direction of the prime mover torque, or you can say mechanical torque. Fine. And there is another torque in the air gap called as electromagnetic torque. There is another torque in the air gap called as electromagnetic torque. What is the direction of that electromagnetic torque? Can anybody tell me? Can anybody tell me how is the direction of that electromagnetic torque? It will be opposite to the prime mover torque. It will be opposite to the prime mover torque, right? So opposite to the prime mover torque means I am showing that electromagnetic torque in this direction. I am calling it is TEM. Electromagnetic torque is TEM. Right. Next thing. Next thing. In which direction the rotor will rotate here? In which direction the rotor will rotate? Is it in the direction of prime mover torque or electromagnetic torque generally? Tell me please. In the direction of the prime mover torque only, the rotor is going to be rotated in case of the synchronous generator. So this is the direction of rotation of rotor with some speed. I am calling it as omega. Calling that as omega. Fine. Next thing. Next. We are going to write first torque balance equation here. Torque balance equation. What is the input torque here? TPM is the input torque. What is the output torque? PM is the output torque. And there is some loss of torque in the machine. There is some loss of torque in the machine. Maybe due to inertia. Inertia means you can feel weight of the rotor. Or else we have some loss of torque due to friction. Loss of torque due to friction, right? Viscous friction, we can say sometimes. Okay, so I'll say torque balance equation first. Torque balance equation. Prime mover torque, so called input torque equals to output torque electromagnetic plus TJ, loss of torque due to inertia, plus TB, loss of torque due to friction. Write this one. Loss of torque due to inertia. So this is loss of torque due to friction. Loss of torque due to friction. Yeah, friction means which friction it is? Friction is okay. Which friction is that? Is it electrical friction or mechanical friction? Electrical friction or mechanical friction? Both. Mechanical friction will come due to windage effect, air circulation and all. That will cause a mechanical friction. Electrical friction is due to damper bars. Electrical friction is due to, because whenever the speed is not equals to synchronous speed, there is a chance of having some induced EMF in the damper bars, right? That will cause some current. It will produce some torque. That is a damper bar torque. The damper bar torque is going to be taken into this damping torque. Damping torque. This TB can also be called sometimes as damping torque. Damping torque produced by friction. Friction in the sense, as we said just now, it is electrical friction, or we can say it is mechanical friction. Mechanical friction. That's it. Next, let me write these words in an expanded way. So I'll keep that TPM, prime mover torque first. Please complete it quickly. I will move to next slide. Please complete it quickly. I will move to next slide. So prime mover torque here, first term. Second term is electromagnetic torque. And whatever the TJ we have written, that I am calling as J into d omega by dt. J into d omega by dt, where J is moment of inertia. moment of inertia of the rotor. Moment of inertia of rotor body. Rotor body. Generally, these units will be in terms of kilogram meter square. Kilogram meter square. And we have the other term as TB, na? TB, that we are going to call as B into d omega by dt. B into d omega by dt. Right? So that B is going to be called as B. B is going to be called as damping coefficient. Damping coefficient. Damping coefficient. Okay. So simply you multiply with omega s, so-called synchronous speed on both sides of equation number 1. Multiply with omega s on both sides. Omega s on both sides. Yeah, if you multiply with omega s on both sides, you'll have omega s into TPM here. Next, omega s into EM plus J into omega s multiplied to d omega by dt plus B into omega s multiplied with, I'm really sorry, it's not d omega by dt. By mistake, I have written. Please kindly see in equation 1, it is B into omega only. B into omega. Okay? Please kindly modify that. Please kindly modify that term in the equation number 1. B into omega. B into omega. Okay, next one. What is it omega s into TPM here? What is omega s into TPM? This is nothing but mechanical input PS. Mechanical input PS. And omega s into TM is the electrical power output PE. Electrical power output PE. Simple. Electrical power output PE. And you see here, listen. We have one term here, J into omega s. J is what? Moment of inertia. Okay. What is omega s here? Angular speed. Or you say angular velocity. Angular velocity. So moment of inertia into angular velocity. This we are going to call with a letter M, which is going to be known as angular momentum of the rotor body. Angular momentum of the rotor body, M. So I'm writing on the next. Angular momentum. Angular momentum of the rotor body, M, which is nothing but J into omega s. J into omega s. Next term, we have that B into omega s. B into omega s. That I'm going to call as some factor D. Damping coefficient only multiplied with omega s. That I'm calling as D here. That we are calling as D. Yeah. Please complete it. And I will rewrite this equation now. Rewrite this equation with this modified terminologies. Okay. Fine. So taking up in the next slide. So mechanical input PS is equals to electrical output PE plus M into d omega by dt plus d into omega. D into omega. Like this, we are going to get the. Okay. Now we are going to neglect the damping. See, this is one of the common assumption. It's one of the common and general assumption to be considered in the whole transient stability analysis. Any method you follow, is it solving swing equation or equilibrium criteria method, which we discuss further. Any method you follow doesn't matter. Always we are going to assume that there is no damping for the machine, right? So let us assume the machine does not have any damping. Does not have any damping. So if that's the case, we are going to assume that D is equals to no damping for the machine. Means we are considering the system as undamped system. We are considering the system as undamped system analysis. Undamped system analysis. Okay, next. So I can write this mechanical input is equals to electrical power output plus M into d omega by dt. So what you will get, M into d omega by dt equals to mechanical input minus electrical power output. M into d omega by dt is equals to mechanical input minus electrical power output. Okay. So this is the This is one type of swing equation. This is one type of swing equation. M into d omega by dt equals to mechanical input minus electrical output. Okay, let's think about that rotor diagram and all, how this omega is going to be replaced. That we are going to discuss further. See, particularly, we are here to derive the swing equation for a synchronous generator connected to infinite bus bar. For a synchronous generator connected to infinite bus bar. That you have to keep in mind. Yeah, let us show that. For example, this is one synchronous generator which we are discussing now, connected to infinite bus. And what do you mean by infinite bus? We said infinite bus is nothing but infinite machine. Infinite bus is nothing but infinite machine where this generator will have an induced EMF as E at an angle delta. Infinite machine will have an induced EMF as V at an angle 0. Already we discussed a little about the rotor axis of infinite machine, rotor axis of generator. These things we have discussed, I think, earlier in the beginning phasor diagram where I explained the rotor angular difference. Rotor angular difference. Yeah. Next thing. Just look here. See, in the whole transient stability analysis, one of the common assumptions is that we are not going to consider the damping in the system, as well as we are not going to consider the losses in the system. The machine is going to be assumed as a lossless machine in the complete study. Okay, fine. See, look here. So I am showing first the rotor axis of infinite machine here. This is the rotor axis of infinite machine. Just write it. Rotor axis of infinite machine. Rotor axis of the infinite machine. Okay. Now, how is the rotor axis of your generator? How is the rotor axis of your generator? Anybody please tell me? How is the rotor axis of our generator? Is it in leading or lagging? Rotor axis of our generator, is it in leading or lagging? Leading. Okay, good. So I'm showing that rotor axis of our generator on which we want to do transient stability analysis might be like this. This is rotor axis of generator. And the angular difference between these two that we are calling as delta. The angular difference between these two is delta. Next thing. Tell me. Simple question again. Rotor axis of infinite machine. Rotor axis of infinite machine, or you say rotor of infinite machine. Will it rotate always at synchronous speed? Rotor of infinite machine, will it rotate always at synchronous speed? Yes or no? Yes. Always, infinite machine rotor will rotate at synchronous speed. Good. So I'm showing it will rotate always at omega s, synchronous speed. The generator, it may rotate at synchronous speed, may not rotate at synchronous speed. Okay. See, if it is also rotating at synchronous speed, then I can say the generator was properly synchronized to the infinite bus bar. Generator was properly synchronized to infinite bus bar. But as we are doing that transient study now, let us assume that it is rotating at a speed of omega, may or may not be equals to synchronous speed. May or may not be equals to synchronous speed. I said simply it is omega. Okay, next thing. Listen. This is one place where you have doubt. Just observe here. See, always this rotor axis of infinite machine is rotating at synchronous speed. So I will be choosing this as reference. Can I? Because this speed is always fixed. As this speed is always fixed, we are going to assume that this as our reference. Is it correct or not? With reference of that only, I am going to check the remaining rotors position in the system. Because of the disturbance. So I'm going to assume this one as synchronously rotating reference frame. Synchronously rotating reference frame. Kindly observe the word. So it is simply the reference for the rotating phasors or rotating vectors. It's simply a reference for the phasors. Which are rotating in the direction what we have shown. Okay, it's a very silly question, but very costly one to understand. Strictly speaking, many of you will have a doubt in this. Very silly question. How you know that this rotor is rotating at omega, and this rotor is rotating at omega s. Tell me please, how come you know? How come you know that? First generator is rotating at omega, second generator is rotating at omega s. Second machine is rotating at omega s. How? Tachometer. Good. Tachometer is one technique. Tachometer measurement. Tachometer measurement means will we stay static while you are measuring the speed of this generator? Will we say static now? Yes or no? Will we say static? Nobody is responding. Yes. Yeah. We have to say static after saying outside static, and we have to say that generator is rotating at omega speed and the infinite machine is rotating at omega s speed. Okay. So for that purpose, I am considering one static reference frame here. Static reference frame. Kindly observe this word, what I am saying. This is one static reference frame, or you can say fixed reference frame. Static or fixed reference frame. Static reference frame, or you can call it as fixed reference frame. Fixed reference frame. So with respect to the fixed reference frame, we say generator is rotating at a speed of omega, infinite machine is rotating at a speed of omega s. Okay. I think all of you clear about this one. All of you clear about this one? Next thing. Listen please. I will be showing the rotor diagram of generator. I'm showing the rotor diagram of generator just for the sake of clarity only. Just I'll show some rotor body. Right? So like this. Showing the rotor body. Right. So it's the rotor body. Next one. Look here. See the position of the rotor, what we are studying. Yeah, one more thing I want to give this clarity. From this point onwards, anywhere, if I say simply rotor, what is that rotor you have to assume? Generator rotor. You have to assume that is a generator rotor. If I say simply rotor speed, you have to say generator speed only. Okay, you should not consider for infinite bus in the general terminology. Okay, the rotor is making an angle of theta with respect to static reference frame. This rotor is making an angle of theta with respect to static reference frame. The theta we are going to call as angular position of the rotor body. Theta we are going to name as angular position of rotor body. Okay, angular position of the rotor body. See, the theta what we are having here, that is angular position of the rotor body. Then simply, what is the d theta by dt? Rate of change in the angular position. Rate of change in the angular position, d theta by dt, that is nothing but speed, omega. So I'll write in the next slide better. So omega, rotor speed, is nothing but rate of change in the position. Rate of change in the angular position. Next thing. Look here, look here. You see, this gap, this angle maybe. See, actually, this infinite motion rotor is rotating at omega s speed. Omega s speed. What are the units of omega s? Radian by second. Radian by second. We need this angle, right? We need this angle. That angle will be obviously omega s into time. Omega s is in radian by second multiplied with time will give radians. That is the angle here, right? So this will be obviously omega s into time. Omega s into time. Now, next thing, next thing. What will happen if generator is also rotating at synchronous speed? Then nothing will happen, then it is synchronized. That's it. What's the doubt you have, Sunil, again? It will be synchronized, that's it. Look here, please. Now, you know, this angle is rotor angle delta we have mentioned earlier. This angle we mentioned as rotor angle delta. Rotor angle difference, or you say simply rotor angle also in the general terminology. And this whole angle we said position theta, and this angle we have taken as omega s into time. Then from this one, you can say theta is equals to delta plus omega s into time. Okay. So from this, you can write theta angular position is nothing but delta plus omega s into time. Delta plus omega s into time. A static reference frame. That's what I said. It is simple one, but difficult to understand. It is simple one, but difficult to understand. That's what I said. You are not concentrating. Please listen here what I am saying. You. One rotor is rotating, you are just observing. You are just observing that one rotor is rotating. With how much speed it is rotating? Standing outside, you will tell, right? By standing outside, you will say that that rotor is rotating at certain speed. That is this reference, what we are saying. Static reference means fixed reference frame. Fixed reference frame. By standing on the fixed reference frame, I will say the generator rotor is rotating at omega, infinite motion rotor is rotating at omega s. Okay? Static or fixed reference frame. It won't rotate along with these two. These two only rotates the phasor diagram. Clear? Yeah. Next thing. See, in this, theta is a variable with respect to time. Delta is also variable with respect to time. Omega s is constant. Now, you go for differentiation of this equation with respect to time. Let us say the earlier equation, this equation you assume as number. This equation you assume as number. Differentiate. This is equation number 3. Okay. Differentiate equation number 3 with respect to time. After doing that, d theta by dt you get on one side. Other side you get d delta by dt plus omega s into time differentiation with respect to time will give omega s. Will give omega s. Okay, this you call equation number 4. Equation number 4. Yeah, you please tell me what is the d theta by dt? What is the d theta by dt? Omega. D theta by dt is nothing but omega. Omega equals to d delta by dt plus omega. Yes. Then rate of change in the angle is rate of change in the rotor angle. Rate of change in the rotor angle is nothing but omega minus omega s. You can say rate of change in the rotor angle is nothing but omega minus omega s. Fine. So this is one equation we have to remember all the time. This is one equation we have to remember all the time. Our stability analysis mostly running along with this statement many times, calculating d delta by dt, right? And based on that, we will be confirming whether the angle is increasing or decreasing with respect to time. Okay, done. Take up the equation 4. Take up the equation 4. Go for one more differentiation of equation 4. Differentiate that equation number 4 again with respect to time. Equation number 4 again with respect to time. What you will get? D square theta by dt square on one side. Other side, d square delta by dt square plus omega s differentiation will be 0 with respect to time. Omega s differentiation will be 0 with respect to time. Fine. And from this one, what we can confirm here is d square theta by dt square value is equals to d square delta by dt square. What do you mean by d square theta by dt square? Name. What is that name? D square theta by dt square we can give. This is going to be called as rotor body acceleration. Theta is the angular position of rotor body, right? Theta is the angular position of rotor body, and the d square theta by dt square is going to be called as rotor body acceleration. Rotor body acceleration. Rotor body acceleration. And what is the d square delta by dt square? What is the d square delta by dt square? That is going to be called as rotor angular acceleration. Rotor angular acceleration. See, rotor angular acceleration. Rotor angular acceleration. Rotor body acceleration d square theta by dt square. Rotor angular acceleration is d square theta by dt square here. Okay, now already we derived some equation, right? M d omega by dt equals to Ps minus P. Let us recall this equation number 2 first. Equation number 2, I am recalling. From equation number 2, M d omega by dt you have, right? M d omega by dt. d omega by dt. That omega we are going to keep it as d theta by dt here. Omega we can keep it as d theta by dt. Getting me? Getting me? Very simple. M d omega by dt. Omega you can keep it what? D theta by dt. By keeping that, on the other side, of course, you have mechanical input minus electrical power output. Mechanical input minus electrical power output. And this we can write as M d square theta by dt square equals to mechanical input minus electrical power output. Theta by dt square equals to mechanical input minus electrical power output. And already just now we derived that d square theta by dt square value and d square delta by dt square value, these two are exactly equal. So in place of d square theta by dt square, you can keep d square delta by dt square. D square delta by dt square. Right? This is one equation what you have derived. One equation what you have derived. M d square delta by dt square equals to mechanical input minus electrical power output. Mechanical input minus electrical power output of the alternator. Mechanical input minus electrical power output. Okay. Next. What is the heading we have taken here? What is the heading we have taken? Swing equation, right? Heading is swing equation. What do you mean by the swing equation? Or else, while you want to do transient stability analysis, listen please, listen carefully. While you want to do transient stability analysis, you have to study how the delta is changing with respect to time. We have to get some sort of relationship between the delta variation with respect to time. That is given by this equation, obviously. M d square delta by dt square equals to Ps minus P. This equation is going to define you how the delta angle is going to change with respect to time. This is going to be called as swing equation with respect to rotor angle variation. Okay, so this is going to be called as swing equation with respect to rotor angle. With respect to rotor angle, and it gives delta versus time variation. Delta versus time variation. Delta versus time variation. Okay, next. I want to tell some more words here regarding this swing equation. First one. Look here. See, first one. What is rotor body acceleration? Rotor body acceleration. Simple, very simple word. Rotor body acceleration means d square theta by dt square, right? Rotor body acceleration means d square theta by dt square. I am asking you, is it correct or not? Is it correct or not? D square theta by dt square. That is nothing but d omega by dt also, right? That is nothing but d omega by dt. D omega by dt or d square theta by dt square, both will be equal. Else, if you want, you write first d omega by dt. Omega you replace with d theta by dt. You get d square theta by dt square. What is that now? What is that? Just look at this equation. Look at this equation. D square theta by dt square is equals to Ps minus Pe by M. Ps minus Pe by M. M is the angular momentum of rotor body. M is the angular momentum of the rotor body. Generally, this angular momentum of rotor body is going to be assumed as constant. This angular momentum of rotor body will be assumed as constant. Assumed as constant. Now tell me please, who is going to decide the rotor body acceleration here? Who is going to decide the rotor body acceleration here? That is decided by mechanical input minus electrical output. Mechanical input minus electrical output. This value will decide the rotor body acceleration, and that we are accelerating power. Accelerating power. Okay, so this is a power. This is a power. Simple. It's the input power minus output power. Input power minus output power. This is a value which is going to decide the rotor body acceleration. Okay, yeah. So accelerating power. Accelerating power. We will indicate this with a letter PA, which is mechanical input minus electrical power output. Mechanical power input minus electrical power output. This is one thing. This one. Second one. Second point in the conclusions of swing equation. In the conclusions of swing equation, we are thinking about the second point. Yeah. Second point I'm going to tell. Just listen. Just listen. See, what is the nature of the swing equation here? What is the nature of swing equation with respect to mathematical terms I want? With respect to mathematical terms I want. Is it differential equation? Yes, because I am finding d square delta by dt square. Second order. It's a second order differential equation. That's one thing what we can confirm. Second order differential equation. Is it linear or non-linear? Is it a linear differential equation or non-linear differential equation? Yeah, generally, in mathematical terms, just observe here. For example, if I have one function like dx by dx by dt, let's say dx by dt is a function of x. Look my words, please. Look my words, please. Dx by dt, first differential only I am considering. Dx by dt, it's a function of x. Function of x. You see, when we are going to say this equation is linear or non-linear, listen to my words first. When we can say this equation, this differential equation, what I have written on the screen, is a linear equation or non-linear equation, means that depends upon this function of x value. Function of x value. For example, if the function of x is non-linear, the function of x is non-linear, then I can say this differential equation is a non-linear differential equation. Then we can say this differential equation is non-linear differential equation. All of you understanding this one? For example, if the function of x what you have written, if that is linear one, function of x is linear, then your dx by dt will be linear differential equation we have to write. That dx by dt we have to write it as linear differential equation. All of you getting my words? All of you getting my words? Now, if you look at the swing equation here, let me write here, swing equation, it is m, okay, d square delta by dt square is equals to mechanical input minus, what is it, electrical output we can write? What is it, electrical output you can write? How will we know, sir, which is linear? That's what I said, no, f of x. If that f of x is, let us say, f of x equals to x, whether that x is a linear variation or not, yes, then this one is a linear differential equation. If f of x is, let's say x square is non-linear, right? Then obviously the whole differential equation will come to be non-linear. That's what I said. It depends upon that f of x, we have to decide. If f of x is linear one, then the whole equation is linear. If it is non-linear, whole equation is non-linear. Yeah, you please tell me, what is electrical power? What is electrical power PE? That is nothing but P maximum sine delta. Electrical power PE is nothing but P maximum sine delta. See, here, you can observe that d square delta by dt square, you take that m also to the other side, m also to the other side. You are having this function as f of delta, right? D square delta by dt square is equals to function of delta. How is that function of delta now? Is it linear or non-linear? How is it function of delta? Please tell me. Please tell me. Is it linear or non-linear? Definitely non-linear because of sign. See, as this function of delta is non-linear one, definitely I can say this swing equation is a non-linear differential equation. Swing equation is a non-linear differential equation, we can say. Okay, let me move to the next slide to write up that comment. So swing equation is non-linear second order differential equation. Second order differential equation. Non-linear second order differential equation. What is the problem of this equation actually? What's the problem of this non-linear second order differential equation? We can't give a direct solution for this one. We can't give a direct solution for this one. In the sense, it is not possible to integrate this equation directly. It's not possible to integrate this equation directly. Means direct integration techniques, what you might have studied, may not be applicable on this one. But we can integrate this equation. We can integrate this equation for a given numerical problem. If you give some numbers to me, you give some problem with some numbers, then I will try to integrate this one by using numerical integration techniques. Numerical integration techniques. Okay, so that implies it is not possible to do direct integration for this equation. Direct integration for this equation. It can be solved. By using numerical integration techniques. Numerical integration methods. Integration methods, or you can say integration techniques. Numerical integration techniques. Examples for these numerical integration techniques are RK method fourth order, right? And we have some method like modified Euler's method. Okay, and we have some technique like step-by-step solution. So these are some techniques. Which we are going to use to solve this one. But anyhow, in our GATE syllabus, as well as in the IES prelims point of view, we don't have this type of technique. Numerical integration technique we don't have in the syllabus. Okay, next thing. Second point we have discussed till now in the swing equation. First point we said regarding accelerating power. Second point we said regarding the nature of the swing equation mathematically. Third point I am going to tell. Third point here. What is M? So-called angular momentum. What is the equation for M here? Observing the swing equation once. This is your swing equation, right? M, what you can write from this? M, Ps minus Pe by d square delta by dt square. M is equals to Ps minus Pe by d square delta by dt square. Ps minus Pe is nothing but accelerating power. Denominator d square delta by dt square. Like this. Pa by d square delta by dt square. Next one. What will be the units of Pa? You tell me in the absolute domain. Absolute domain, what's the units of Pa? Power, na? Megawatt. Pa is in terms of megawatt power. What will be the denominator units here? Electrical radians by second square. Electrical radian by second square, you can say. Now, what will be the overall units of this ratio? megawatt second square by electrical radians. You can say megawatt second square by electrical radians. Okay, else you can call the units of m here in another way. Units of m, units of angular momentum. Megawatt second square by electrical radian is 1 unit we have written just now. Else you can call this one megawatt into second. Megawatt into second is a megajoule. Megawatt into second is megajoule. So it is megajoule second by electrical radian. This unit can also be used for this. That unit can also be used for this. Not only in electrical domain, not only in the write it in the mechanical domain also, like mechanical radian, mechanical degree, like that also you can write. Okay, I will discuss about this m units in detail in the later studies, but right now the units of m will be in this manner: megawatt second square by electrical radian or megajoule second by electrical radian, you can say. Fine. So this is about swing equation of the synchronous generator. Swing equation of synchronous generator. In the similar lines, we'll take up the swing equation of the synchronous motor also a bit quickly. Okay. After completing that, I'll tell you what we are going to do further. Yeah. Let us say next slide. Next slide I'm taking up. Swing equation for synchronous motor. Swing equation for synchronous motor. Yeah. Swing equation for the synchronous motor. Yeah, I'm showing case 2. Somebody is asking me. This one only case 2. Abhijit, this is case 2. Case 2. You are writing, please complete it quickly. Again, synchronous motor means, I will say synchronous motor connected to infinite bus bar. Synchronous motor connected to infinite bus bar. Let us see. Again, I will show that rotor diagram quickly, because I can complete this one a bit quick and it is easy to understand. That's why I'm saying I'm taking this synchronous motor also here itself at a stretch. Okay, so this is the rotor body and associating shaft, I can say. Rotor body with some what we call angular momentum of J, right? It's a shaft. We have taken shaft. And see, for this synchronous motor, we have some electrical power input P, and we are having some mechanical load or mechanical power output, but still I am using that word as PS. For my convenience, I am using that word as PS, but sometimes in textbooks, the people will use P mechanical like that. Okay, fine. Next thing. See, because of this electrical power input, what we are giving, there is some electromagnetic torque created in the air gap. There is some electromagnetic torque created in the air gap. So I am showing that electromagnetic torque in this particular direction. TEM, electromagnetic torque in that particular direction. How will be the load torque action? In what direction load torque will be acting? Anybody please tell me? Yes, Ramakrishna. In which direction? Definitely it will be in opposite direction, right? Opposite direction. So in this direction, we get the load torque. Load torque, else you can say mechanical torque, or you can say TS. TS, T mechanical, any notation you use according to your comfort level. Okay, please tell me in the air gap, we have two torques. In which torque direction the rotor is rotating? In which torque direction the rotor is rotating? Anybody, please tell me. Which torque direction the rotor is rotating? Definitely in the direction of the electromagnetic torque, because that's the input. That's the input. So in this direction, the rotor is rotating at a speed of omega. Rotor is rotating at a speed of omega. Can you write now what is that torque balance equation now? Torque balance equation is what? Electromagnetic torque input is equals to prime mover torque output, sorry, mechanical load torque output plus loss of torque due to inertia plus loss of torque due to friction. Same terminology, same terminology. We have some input torque to the machine or to the rotating body, input torque, and there is some output torque, and there is some loss of torque due to its inertia of the body, as well as some loss of torque due to friction. That's it. So you can call if you want, this is input, electromagnetic torque input, and this is output torque, and these two are losses. Okay, I will write this one in the expanded way as we have written earlier. Let me write in the expanded way. Please complete it if you are still doing it. Please complete this one quickly. Yeah, so I can say electromagnetic torque is nothing but mechanical torque plus J d omega by dt plus B into omega. J d omega by dt plus B into omega. Now you multiply with omega s on both sides. Multiply with omega s on both sides. Both sides. Okay. So if you multiply with omega s, so I can say omega s into Tm, omega s into Ts, again omega s into J d omega by dt plus omega s into B into omega. Simple. And this omega s into Tm is electrical power PE. Omega s into Ts is PS. Omega s into J is M, angular momentum. And this we are going to call as D, damping coefficient. Now you can write from this electrical power input equals to mechanical output plus M d omega by dt plus D into omega. D into omega. And again, we neglect the damping here. It's a lossless. All the cases, Sunil, all the cases we are assuming this as lossless only. Again, we neglect that damping D. By neglecting the damping, you can write now M d omega by dt equals to input minus output. Input is electrical, output is mechanical in this case. Right? So I can write now M d omega by dt is equals to electrical power input minus mechanical power output. Electrical power input minus mechanical power output. Okay. So now, yeah, you write here clearly what written. By neglecting damping in the machine, by neglecting damping in the machine, that is P is equals to G. We can write this. Okay. So next, I will take up the rotor diagram in the similar manners of previous discussion. Rotor diagram and all. Then we will rewrite this one in terms of delta. In terms of delta, as well as in terms of theta, angular position of the rotor. Look here. So this is the infinite bus bar, and this is our synchronous motor. Right? So this is an infinite machine, and this is our synchronous motor. Right. See, this infinite bus voltage is mod V at an angle 0 degree. Internal EMF of motor is mod E at an angle minus delta. Mod E at an angle of minus delta. That's the internal EMF of the motor. Internal EMF of the motor. Okay. Now, first I'll take reference. That's the infinite bus rotor axis, which is always rotating at synchronous speed. We have discussed already, but still I am repeating. Kindly observe these things. Is the rotor axis of infinite machine, which will always rotate at synchronous speed. This direction I am taking, always rotating at synchronous speed. Next thing. A rotor of synchronous motor. Rotor of synchronous motor is in lagging. Rotor of the synchronous motor is in lagging by how much angle? Delta. So I can say this is a rotor axis of synchronous motor. Rotor axis of synchronous motor. It's in lagging by how much angle you are saying now? Delta is the angle. Delta. And this will rotate at a speed of omega. This will rotate at a speed of omega. May not be equals to synchronous speed all the time. May not be equals to synchronous speed all the time. Okay, for your understanding, I will show that rotor diagram and all. Stop, sir. This is a rotor diagram I am showing, synchronous motor. Rotor. Right. So that's the rotor diagram of synchronous motor. Next thing. We have to take some fixed reference frame or static reference frame just for the sake of analysis. This is some fixed reference frame I have considered, or static reference frame, or static reference frame. Fixed or static reference frame. So again, we will take some angle theta here. This is angle theta, which is deciding the position of the rotor. Rotor means I said what we are discussing, finite machine. Synchronous motor rotor itself is called as a rotor in the analysis, right? Theta, angular position of rotor. Angular position of rotor. Angular position of rotor. Next one. See, this is rotating at omega s, so-called infinite machine axis, rotating at omega s. Units will be radian by second. Radian by second. Multiply with time. You get in radians. So this whole angle what we have here is going to be called as omega s into time. Okay. And this angle we are saying as delta. This angle we are saying as delta. Delta. Okay. Now from this. Already you know d theta by dt equals to omega. Na? Already you know d theta by dt is nothing but omega, which is speed of the rotor of synchronous motor. Speed of the rotor of synchronous motor. Okay, next thing. Let's write that combination, the term. Omega s into time is equals to delta plus theta, you can write. Okay, you please complete it quickly. Please complete it. All of you have understood this one? Please tell me once. Have you understood this one? First we have taken the reference. Then we have taken the what we call rotor axis of the machine on which you are doing the analysis. So called synchronous motor rotor. Good. What is the name of this one we mentioned earlier? What's the name of this one? Rotor axis of infinite machine is nothing but synchronously rotating reference frame. Synchronously rotating reference frame. Sir, why lagging? Why lagging means that depends upon the power flow. Mr. Anonymous attendee, power is flowing from the infinite bus to motor, right? Infinite bus to motor, we have the power flow. So obviously that motor axis will be in lagging with respect to infinite machine. Have you understood this, Diveshri? That depends upon the power flow. Next thing. Let's write here omega s into time is equals to delta plus theta. Okay, you go for the first differentiation of this with respect to time. Differentiate above equation with respect to time. Then what you get is omega is here, and you have d delta by dt plus d theta by dt. Omega s is equals to d delta by dt plus d theta by dt. You call this is equation number 2 in this study. Equation number 2, you call it equation number 2. Okay, now omega s is equals to d delta by dt plus what you can write the d theta by dt. What you can write the d theta by dt. That is nothing but omega. And respect to generator flow from generator to infinite bus. So leading generator. Yes, yes, Pramod. Yes. Respect to power flow. Respect to power flow, it will be. Yeah. So this is omega. That is rotor speed omega. Now, what is the value of d delta by dt from this one? Anybody tell me what is the d delta by dt here? Omega s minus omega. Omega s minus omega. Right. So this is the change in the rotor angle with respect to time. Change in the rotor angle with respect to time. That is omega s minus omega we are getting. Earlier, in case of generator, what you got? Anybody tell me, please? Earlier, in case of generator, what you got? D delta by dt is equals to, let's check, omega minus omega s. Earlier, we got omega minus omega s, but now you are getting that as omega s minus omega. Omega s minus omega. Fine. This difference you have to observe. This difference. Next thing. Next thing. So let's say take up the one more differential equation. There's a differentiation for equation 2. Take up one more differentiation for equation number 2. Differentiate equation number 2 with respect to time. Means 0. Omega s differentiation is 0. Next you get d square delta by dt square plus d square theta by dt square. And now you can write from this d square theta by dt square value will come by minus d square delta by dt square. D square delta by dt square. D square theta by dt square equals to negative of d square delta by dt square. The d square theta by dt square already we mentioned rotor body acceleration. Rotor body acceleration. Rotor body acceleration is equals to negative value of angular acceleration. Angular acceleration is negative value of rotor angular acceleration. Earlier case, both are equal. D square theta by dt square, d square delta by dt square, both are exactly equal. Okay, next. Let us take up the equation 1. What is equation 1 we have considered? Okay, this one. The m d omega by dt you have that you take as equation number 1. Equation number 1. Now simply omega you keep as d theta by dt, and you get m d square theta by dt square equals to electrical input minus mechanical output. Okay. Next slide I can say from equation number 1. From equation number 1, m d omega by dt means d by dt of d theta by dt equals to electrical power input minus mechanical power output. So you can call here m d square theta by dt square equals to electrical input minus mechanical output. Electrical power input minus mechanical power output. So this is the swing equation. This is the swing equation with respect to rotor body. Swing equation with respect to rotor body. Okay, because I am taking that angular position of rotor here. The angular position of rotor I am taking. So it is a swing equation with respect to rotor body. Rotor body. Omega s is constant, right? Omega s is constant. Then differentiation of that omega s will be 0. Omega s is constant, so obviously differentiation will be 0. Okay, what is d square theta by dt square here? Look this one. D square theta by dt square is negative of d square delta by dt square. So I can say m into minus d square delta by dt square equals to electrical power input minus mechanical power output. From this, m into d square delta by dt square equals to mechanical output minus electrical input. mechanical output minus electrical input. So this is one way of representing the swing equation. In case of synchronous motor, this is swing equation with respect to rotor angle. Swing equation, rotor angle, rotor angle. Swing equation with respect to rotor angle. Okay. I will come back within 1 minute. Please write it. Come back within 1 minute. Yeah. Just have a look now. Have a look now. See, if anybody asks you, in this case, particularly in case of synchronous motor, what is accelerating power? What is accelerating power in case of synchronous motor? What do you have to answer? What is accelerating power? What do you have to answer? That is power which is causing for acceleration for rotor body movement. The value of power which is causing for the acceleration in the rotor body, that we have to name it as accelerating power. It will be electrical input minus mechanical output we have to call. Not that mechanical minus electrical what we got in case of swing equation of the rotor angle. All of you getting my point? So in case of synchronous motor, accelerating power PA is equals to electrical power input minus mechanical power output, we should say. It will be the difference between electrical input and mechanical output. Electrical input and mechanical output. Yeah. So I think all of you getting this one? Next thing. Forget about the synchronous motor and all. We will be continuing our discussion only with respect to synchronous generator. We are going to continue our discussion only with respect to synchronous generator. So what is the generator swing equation we have derived? Generator swing equation md square delta by dt square is equals to ps minus pt. Else md square theta by dt square d square theta by dt square equals to ps minus pt. One more, d delta by dt omega minus omega s, omega minus omega s, and accelerated input minus electrical power output. Only these terms we are going to discuss up to some extent. At the end of this stability analysis, we'll discuss about synchronous motor also, one type of disturbance. Clear? Okay. Next, listen to my words, what I'm saying now. Listen. See, why we are deriving the swing equation? Can anybody tell? What is the necessity of deriving the swing equation here? Anybody? Necessity of deriving the swing equation. What is that? To do transient stability analysis, that I know, to do transient stability analysis, to know delta, how it is changing with respect to time. To know how the delta is going to change with respect to time. Okay. Can we do steady state stability analysis by using swing equation? Can we do steady state stability analysis by using swing equation? Yes or no? Is it possible or not? Yes. Yes. Why can't it be? Why can't it be? We can do, if you want, you can do steady state stability analysis by using swing equation also. See, after all, the swing equation is going to tell how the delta is going to change with respect to time because of disturbance. Is it a small disturbance or high disturbance? Whatever it is, it will give its own result, right? Yes or no? But what I said earlier is, doing the steady state stability analysis with the help of swing equation may be difficult one. Maybe difficult one. So you no need to study delta versus time, just to tell me whether the system is stable or unstable in the steady state. That's it, we said. But if anybody forced you to do steady state stability analysis, and if you want to find delta versus time exactly, you can do that by using the swing equation. Okay, because it's a generalized technique of doing the what we call exactly Sai Charan. Doing stability analysis, whether it is a steady state or transient, whatever it is, by using swing equation is an exact study. It will be the exact study only. Yes. Yeah, fine. Next, let's take that heading what I said till now. Steady state stability analysis. Steady state stability analysis by using swing equation. Steady state stability analysis by using swing equation. Okay, swing equation. Else this heading what I said here. After steady state, why synchronous machine speed is not becoming synchronous speed? Steady state means what? Continuous disturbance, right? Steady state means we have a continuous disturbance. If you have a continuous disturbance, definitely the speed will not be equal to synchronous speed. That's the reason why the frequency of Indian power system will not be maintained always constant at 50 Hz. Why it is continuously changing? For example, if you look at any regional load dispatch center website, maybe SRLDC, or you go with the POSOCO, just to look at that website, they used to print the frequency with respect to time, which is continuously changing, grid frequency. Why it is not maintained as 50 Hz? Because we are dealing with the disturbances all the time, even in the steady state also. Following. So even you say in the steady state, the speed of machines will not be synchronous all the time. Definitely the speeds are changing, but we have a narrow range of variation. That's the thing we have to identify. Narrow range of variation. For example, 1500 RPM is a synchronous speed. The machine may rotate in the range of 1498 to 1502 RPM. In that range, it is going to rotate in the steady state operation because of the small disturbances. Okay? Yeah, fine. So at home, we do get exactly 58. No, Jadav, it's impossible. It is impossible to say exactly your frequency is 50 Hz. Mostly, Pramod, that's what I said. No, doing steady state stability analysis with power equations is easy. That's why we have done it. Now we are interested to know in the steady state by using swing equation. Okay. This heading sometimes can be called as solving swing equation for small disturbances. This is one type of heading you can find in some textbooks. Other type of heading, what you can find for the same is linearizing the non-linear swing equation. non-linear swing equation. Linearizing the non-linear swing equation. Okay. Next, let's continue. Let's continue. So I'm taking up again a synchronous generator connected to infinite bus bar, something like this. Infinite bus bar, and this is a mechanical input. PS I am showing mechanical input. I am showing that as PS, and we have some electrical output as PE. P, which is a function of delta. P is a function of delta, and let me call this machine induced EMF is mod at an angle delta. Infinite bus voltage mod at an angle 0. Impedance of this machine is JXD steady state. JXD steady state impedance. A swing and oscillation both are same. Swing or oscillation both will be same. Yeah. Next thing. What is the expression for the electrical power PE? That is mod E into mod V by XD into sine of delta minus 0. So it will be sine delta. You can call it is P maximum sine delta. P maximum sine delta. So you can call this is PE, which is a function of delta. PE, which is a function of delta. So P maximum sine delta V. Next. See this machine, what we are having now, is having an angular momentum of M. That machine is having an angular momentum of M, we are saying. Yeah. Fine. Next. These are some equations, only equations. I'll take initial conditions now. Initial conditions are rotor angle is delta naught. Okay. And electrical power output, what we have in that initial condition, and the mechanical input, both are exactly equal. That's right. Initial conditions. Initial conditions. First, rotor angle delta naught. Rotor angle is delta naught. And electrical power output. Electrical power output. So I can call it is P of delta naught here, which is nothing but P maximum sine delta naught. P maximum sine delta naught. That's the electrical power output. Electrical power output P of delta naught is P maximum sine delta naught. Steam input, or you can say mechanical input, that is PS. These two are exactly equal in that initial condition. Mechanical input and initial electrical power outputs are exactly equal. Mechanical input and initial electrical power outputs are exactly equal. That's the thing. Next thing. Next. Let's write swing equation also in the initial condition. Swing equation also in the initial condition means M d square delta by dt square is equals to PS minus PE. Na? PS minus PE. Listen to me. Don't write, please. Don't write. Listen. M d square delta by dt square. I want to take up that M d square delta by dt square at an angle of delta naught. Okay. And this PE we are going to keep it as P maximum sine delta naught. P maximum sine delta naught. So PS is a mechanical input to the machine, what we are giving. Initial electrical power output is P maximum sine delta naught. And I already said these two are exactly equal. These two are exactly equal in the initial condition. Then how much is this value to be expected now? 0. That value to be expected will be obviously 0. Clear? Now, in the next case, what I say is small disturbance occurred on the system. Small disturbance occurred in the system because of that the rotor angle is changed. Rotor angle is changed, or you say increased by a value delta delta. A value delta delta. Again, the delta delta is a function of time. Delta delta is a function of time. I'll tell you. Look here. Small disturbance. Small disturbance. Because of the small disturbance, rotor angle was increased by delta of t. Rotor angle was increased by delta of t. It's a very small angle. It's a very small angle variation. Now, what will be the new angle? New rotor angle will be, because of the small disturbance, it will come to be delta naught plus delta of t. Delta naught plus delta of t. Means you have to expect now, initial rotor angle is delta naught. Initial rotor angle is delta naught. Above that delta naught, initial rotor angle is delta naught. Above the delta naught, the angle is changed by some value. Angle was changed by some value that we are naming as delta of t. Delta of t. Clear? Now, if you go with that what we call swing equation and all, we can write swing equation m d square delta by dt square value at what angle? Delta naught plus delta. The angle of delta naught plus delta equals to mechanical input minus electrical power output is P maximum sine delta naught plus delta. P maximum sine delta naught plus delta. It may not be Likita, it may not be always increasing, it may decrease also. Okay, I want to expand this equation a little bit. Just go through it now. PS minus P maximum sine delta naught cos delta minus P maximum cos delta naught sine delta. P maximum sine delta naught cos delta minus P maximum cos delta naught sine delta. But the delta is very small. Yesterday also we have done same thing. Delta is very small. If delta is very small, this cos delta is approximated to 1. Delta value was approximated to 1. Sine delta we will be approximating to delta in terms of radians. Delta in terms of radians. Okay? Yeah. So let me write in the next slide. Next slide. Please complete it. Once after completion, please raise your hands. Yeah. So let's say m d square delta by dt square at an angle of delta naught plus delta is equals to mechanical input minus electrical power, PS minus P maximum sine delta naught. One term we have, first term is P maximum sine delta naught minus. What is the second term we have? P maximum cos delta naught into delta in terms of radians. Into delta in terms of radians, you can see. And already I said this PS minus P maximum sine delta naught value was 0. Already I said that PS minus P maximum sine delta naught, that value was 0. Yes or no? Just look here. PS minus P maximum sine delta naught value was 0. That we have replaced. Okay, next. Observe all of you look here. This differential function I am going to rewrite into two terms. Because up to delta naught is a constant angle. Above delta naught, there is a change in the angle by delta. Above the delta naught, there's a change in the angle by delta. That's why I'm going to rewrite the differential term into first term as m d square delta by dt square value at an angle of delta naught plus m d square delta by dt square. Divide into two parts. One is a delta naught, second one is a delta. So as a delta itself is variable, just directly dump into the equation like m d square delta by dt square is equals to, first term is 0, second term minus p maximum cos delta naught multiplied to delta in terms of radians. Delta in terms of radians. PS is mechanical input, right? How it is related to the network, Sai Chiran? How the PS value is related with the network. It is completely within our control, we can say. According to the steam valve opening, how much mechanical input we are giving, that we are able to know. But who is going to decide the electrical power output? That is decided by the network. That's why you get the electrical power in terms of P maximum. In initial CDT, what is that CDT I wrote in the initial conditions? What I have written here? Initial conditions? I don't think so. Anything here. CDT. What is that? Yeah. Let's continue. What is the first term? Can you tell me, please? First term 0. That's what we said. M d square delta by dt square value at the initial angle, that is 0. And you can say this LH is m d square delta by dt square value is nothing but minus p maximum cos delta naught into delta, of course in terms of radians. PS will be remains same. PS will be remains same. Assuming that PS is constant. Initial condition, I have not written anything, right? PS I have not written in terms of P maximum. What is the initial condition? I said initial electrical power in output, mechanical input, electrical power output. These two are equal. That implies no acceleration initially. That's the meaning, Sai Chiran. No acceleration. That is the meaning. Yeah, let's move ahead. See, this is the final equation we got after doing some assumptions and all. That is m d square delta by dt square is equals to minus p maximum cos delta naught into delta. See, this p max is a constant value for a given network. For a given network, p max is constant. Delta naught is the initial angle. Initial angle, right? And this cos delta naught is also constant. Let us take the p maximum cos delta naught as some constant k. So let p max cos delta naught is equals to some constant k. Therefore, m d square delta by dt square value, m d square delta by dt square value is equals to minus k into delta. You please tell me, is it a linear equation or non-linear equation? Yeah. Is it a linear equation or non-linear equation? Of course, it is linear. Of course, this equation will be linear. Why? Why in the sense, again, same principle you have to use. M d square delta by dt square is a function of delta. The function is linear. So hence the whole equation will be linear equation. So this is the linearized non-linear swing equation for small disturbances. It's a linearized form. Linearized form of non-linear swing equation. Non-linear swing equation for small disturbances. Small disturbances. Okay, linearized form of non-linear swing equation for small disturbances. Now you can apply what we call Laplace transform for this one. Yes, you write first m d square delta delta by dt square plus k into delta delta is equals to 0. Is equals to 0. So applying Laplace transform, apply Laplace transform on both sides. On both sides. Applying Laplace transform on both sides will give an equation like m s square plus k into delta delta of s is equals to 0. ms square plus k into delta delta of s is equals to 0. Fine. Why that s term is missing here? Can anybody tell me why that s term is missing? S square term is there. S power 0 is there. K into s power 0. S power 1 is not there. S power 1. Why that s power 1 term is missing? Why? Because we neglected the damping. Because we neglected the damping. For example, if we consider the damping also, then how we are going to get this equation? Next, if damping also considered, considered. So I can say ms square plus d into s plus k. This into delta delta of s is equals to 0. ms square plus ds plus k into delta delta of s equal to 0. Like that, we are going to get the equation if the damping value is also considered. Damping is also considered. What is a characteristic? What is a characteristic equation of this one? Characteristic equation. Nothing but ms square plus ds plus k is equal to 0. ms square plus ds plus k is equals to 0. That is a characteristic equation. And you try to find out the roots of the characteristic equation. Then based on these roots position in the S plane, based on the position of these roots in the S plane, we can decide whether the system is stable or unstable. Yes or no? Right. Write down the roots of this one. Roots of this one. Roots we are writing now. S is equals to minus d plus or minus square root of minus b plus or minus square root of d square minus 4ac is d square minus 4mk by 2m. Like this, you will get roots. Minus d plus or minus square root of d square minus 4mk by 2m. I'll write it into two parts. Okay. First part is minus d by 2m plus or minus square root of this 2m we will take into the square root. This 2m we will take into the square root. It will come like d by 2m whole square minus 4mk by 4m square. Observe this. 2m we are taking into square root means it will become 4m square. 2m whole square it will come. Or else 4m square. So I have written d square by 2m whole square means d by 2m whole square minus 4mk by 2m whole square means 4m square. Do the cancellations. And I will write this yes again. Yes, I'm going to write. S is equals to minus d by 2m plus or minus square root of this is d by 2m whole square minus you see that 4m and 4m will be cancelled out. You get this as k by m. D by 2m whole square minus k by m. K by m. Next thing. See, in this whole equation, you tell me please, which number is variable and which are constants? Which number is variable and which are constants? D, damping coefficient is almost constant. Damping coefficient is almost constant. M, constant. D by 2m whole square, constant. M, constant. What is K? What is K we have defined? P max into cos delta naught, right? P max into cos delta naught is a K what we have assumed. Here, P maximum cos delta naught is K. See, the position of this root, the position of these roots depends upon, listen please, listen to my words please. Depends upon the value of initial condition. What is the initial condition here? That will decide the position of these roots in the system. Okay, so for example, in the case one, if k by m number, this value k by m number is greater than d by 2m whole square, then tell me please, k by m number was greater than d by 2m whole square. Then inside the square root we have a negative sign. Inside the square root you have a negative sign. Negative sign under root means you will get j symbol. And roots will come to be complex conjugates. Roots will come to be complex conjugates. I will say two roots now. First root I am writing S1 root with positive sign. Minus d by 2m plus, you take that j out. Square root of, it will come k by m minus d by 2m whole square. I think all of you getting this way of writing. You might have written these things many times in control systems. Right. So S2 root will be minus d by 2m. I'll take minus sign for this. J square root k by m minus d by 2m whole square. K by m minus d by 2m whole square. So these are the roots we have, S1 and S2. S1 and S2, complex conjugates. Next, for example, if k by m value and d by 2m whole square, these two are exactly equal. If k by m value and d by 2m whole square, both are exactly equal. What you can say from this? Second one, k by m value and d by 2m whole square, if these two are exactly equal, what you can say? Then S1 root will be minus d by 2m. What about S2 root? Also minus d by 2m, right? S1 root is minus d by 2m. S2 root is also minus d by 2m. Real and both are equal. Real and equal. That's one condition. Next one. If k value was 0, if k number what we say is 0, then what will happen? If k is 0, this won't exist, and d by 2m whole square under root means d by 2m. Look here. Third one. If the value of k is equals to 0, then S is equals to minus d by 2m plus or minus d by 2m. Plus or minus d by 2m. So if I take plus, I'll call that is S1 root. If I take minus, I'll call that as S2 root. S2 root is minus d by 2m minus d by 2m. So it will come like minus d by m. That root will come to be minus d by m. S2 root will be minus d by m. Yeah. Next. For example, if the k value was negative, then what will happen? K value was negative. Tell me please. If k is negative, what will happen? If k is negative, already minus sign is there, and if k is negative, negative will be cancelled and plus. Means d by 2m whole square plus some number. D by 2m whole square plus some number under root. it will come as a positive number only. You don't get J sign. You don't get J sign. Okay. Then I have to write roots as it is of original. As it is of original. If k is less than 0 or if k is negative L. That's right. Fourth one. Fourth one I am saying. K value was less than 0 or k is negative. K is negative. Then S1 root will be minus d by 2m plus square root of d by 2m whole square minus k by m. Minus k by m. We observe now, we observe here what? This d by 2m whole square minus k by m if we calculate. Already k is negative. Look all of you. Stop writing. Just listen. K is negative. Means d by 2m whole square plus some number you get. D by 2m whole square plus some number under root. Definitely comes as more than d by 2m. Definitely it will be coming as more than d by 2m. So as it is more than d by 2m and you have minus d by 2m, this whole number will turn to positive. Whole number will turn to positive. Turn to positive. Okay. Next, S2. S2. Minus d by 2m minus square root of d by 2m whole square minus k by m. Minus k by m. And this root will be whole negative. Because already both symbols are minus only. Then S2 root is completely negative. S2 root will be completely negative. Okay. Now, simply, I will take one S plane. I'll take one S plane. Yeah. I'll take one S plane. In the S plane, I will be keeping the roots in a sequence. Case 1 roots, case 2, case 3. Yeah, that's all next. It's a S plane. It's a real axis. Imaginary axis. And it's a positive imaginary axis. Negative imaginary axis. Positive real axis. Negative real axis. Okay, done. This is 0 point center. 0 point. Next thing. Okay. Case 1. Roots are complex conjugates. Both are having same real part. But imaginary part will be one and opposite. Real part in the case 1, I am locating at this place. Minus d by 2. Positive imaginary I am showing here. Negative imaginary I am showing here. Positive imaginary means j square root of k by m minus d by 2m whole square. And negative imaginary minus j square root k by m minus d by 2m whole square. Okay, like this way. Now let me think about this root quickly. Yeah. So this is S1 root and this was S2 root. Position of S1 root and S2 root. All of you getting this? Position of the S1 root and S2 root. Next thing. Case 1. Case 2 observe. Case 2. I am showing S2 root in red color. S1 root in red color. S1 root I am showing in red color and S2 root I am showing in a blue color. Let's look back to the cases. Case 2, both roots are same. S1 root is minus d by 2m. S2 root is also same. So this is a place at which both roots will be inclined. This is a place at which both roots will be inclined. Means, listen please, listen all of you, listen all of you. So this is a way how we have to observe. This is a way how we have to observe. Initially, we have some k value. Initially, we have some k value, positive number. With respect to the k, S1 root is lying at this place, S2 root is at this place. Okay. And if k is decreasing, if k value was decreasing, do you have any change in the real axis number? If k is decreasing, do you have any change in the real axis number? Yes or no? No, because it is minus d by 2m, right? Because it is minus d by 2m. No. What will happen to imaginary number? That will decrease. Yes, that will come. Means as a k value was decreasing, this S1 root, what you have shown here, it will move in this direction. It will move in this direction. And whatever the S2 root we have here, that will move in the upward direction like this. S2 root will move in the upward direction. All of you understood this movement of roots? I need your response, please. I need your response. Kindly tell me, have you understood the movement of these roots? For k decrement. For k decrement, the roots will move in that direction. Yeah, good. So, for certain value of k, we are having that k by m equals to d by 2m whole square, and both roots are inclined. Both roots are inclined to this place. Both roots are inclined to this place. Okay. So S1 root is coming in that manner, and S2 root is coming in this manner. Okay, next thing, next thing. I think case 1, case 2 completed up to this point. Case 1, case 2 completed. What is case 3? K equals to 0. If k value was 0, then how is the S 0? What is the S2 root? Minus d by 2a. S1 root, what we have here, if you reduce the k value further and further, if you reduce the k value further and further, S1 root will move in this direction, and finally touches to 0. For how much? How much value? For k equals to 0. Whereas S2 root will move in the negative real axis direction. S2 root will move in the negative real axis direction like this, and it will touch to minus d by m. Minus d by m. So this is the position of the S2 root, and for k equals to 0. And this value was minus d by m. Minus d by m. All of you getting this point? Simple, very, very simple. Very, very simple. If k value was further decrease, whatever the roots we have at the minus d by 2m, one root will move towards the 0 point, other root will move towards the minus d by m point. Now, if k is becoming negative, what will happen? Negative, what will happen to S1 value? Positive. S2 value more and more negative. Means for k value less than 0, the root will move in this direction. For the value of k less than 0, root will move in this direction. Whereas this root will move ahead like this. That root will move ahead in that. For the k value less than 0. Means negative. Yeah. Completed? Tell me, how many roots we have in the system? For the characteristic equation, you can say. For the characteristic equation, how many roots we have? 2 roots. 2 roots. Good. 2 roots. When we will say system is stable, in generally from view of control systems or S-plane, when we will say system is stable, if both roots are existing on the left half of S-plane, both roots S1, S2, both are on the left half of S-plane, then the system will be stable. If any one root among these two, is going into positive real axis, then we can say system will be unstable. Yes or no? Okay. So when when roots are existing only on the left half of S plane, when the roots are existing only on the left half of S plane, for the k value greater than 0, for the k value greater than 0, the roots will lie either on these lines or on this line. That's it. Okay? Yeah, let me write the next slide. The conclusions with respect to stability we are saying. Conclusions with respect to stability analysis. When the system is stable, when the system is unstable, decided by position of the rotor, position of the roots, position of roots, decided by k value. Position of roots is decided by k value. Right. If k value greater than 0, both roots exist on left half of S plane, left half of S plane, system is stable. System is stable. Okay, next one. If k value less than 0, if the k value was less than 0, then what you can say? One of the root, maybe S1, what we are discussing, that is moving into right half of S plane. Other root is on left, that's okay. Other roots are left, okay. Any one root is moving on to right, that is sufficient. One of the root moving on to right half of S plane. Right half of S plane. System is unstable. System is unstable. Okay. Next, if k equals to 0, what you can expect here? K equals to 0, what you are expecting? Anybody tell me, please? If k equals 0, one root, so-called S2 is on left half of S10 minus d by m position. But S1 root is at origin. S1 root is at origin. Means one root is at origin, other root is on the left half of S plane. System is either marginally stable or marginally unstable. Okay? Right. And one root is at origin and other root is on left half of S plane. Left half of S plane. System is marginally stable or marginally unstable. System is marginally stable or marginally unstable. Marginally unstable. System is either marginally stable or you can say marginally unstable. Clear? Only 2 poles you have, that's it. What is the meaning of dominant flow? Only 2 poles. If you have many poles in the system, then you should think about the dominant and non-dominant poles. Yes or no? As if you have only 2 poles in the system, both poles you have to consider in the study. Yeah, let's move ahead. What is this K which is deciding system stability now? What is that K which is deciding system stability? P maximum cos delta naught. Yes or no? That K is nothing but P maximum cos delta naught, which we have considered here. Means what? What is the P maximum cos delta naught name? What is the P maximum cos delta naught name? Synchronizing power coefficient again. Again, we end up with the same result. That's the thing we have to understand here. Again, even though you are doing what we call steady state stability analysis by using swing equation, finally you end up with the same thing what we have discussed in the theory. Means if the P maximum cos delta naught is positive, then the system is stable at that angle. And if it is negative, the system will be unstable at that angle. And if it is 0, the system is marginally stable or marginally unstable at that angle. That's it. I think all of you getting my point what I said. Yes or no? Right. But in the view of examination, sometimes what they will ask is generally most of the times they will give a stable system. they will give a stable system. Means the loading on the system is 50% of P maximum, or 60% of P maximum, 70% of P maximum. Like that they will give. For example, I am asking a simple question. Present loading is 70% of P maximum. Present loading is 70% of P maximum. Whether the system is stable or unstable for small disturbance. Whether the system is stable or unstable for small disturbance. Tell me please. It will be definitely stable, right? It will be definitely stable. That's it. Yes or no? Right. System is stable, but the additional question what they can ask is, what are the frequency of oscillations made by the rotor for small disturbance? What are the frequency of oscillations made by the rotor for the small disturbance? That type of question they can ask. Okay, if they are asking that question, simply you take up this one. You see S1 and S2 minus d by m plus or minus j square root of k by m minus d by 2m whole square. Nah? This term what we have, root of k by m minus d by 2m whole square, this is going to decide the frequency of oscillations made by the rotor. Frequency of oscillations made by the rotor for a small distance. Okay? Yeah. Frequency of oscillations. Frequency of oscillations made by rotor for small disturbances. Small disturbances on a stable system. In bracket you write on a stable system. Omega delta nothing but square root of k by m minus d by 2m whole square. D by 2m whole square. And this will come in radian by second. Come in radian by second. And you, if you want to get that in Hertz, frequency Hertz, F delta 1 by 2 pi square root k by m minus d by 2m whole square in terms of Hertz. Of course, if you want me to write, I'll write k value, which is P maximum cos delta naught. Synchronizing power coefficient. K is nothing but P maximum cos delta. Okay? And you please complete it. Next. What is this we call? What is this diagram? Anybody? Can you give any name for this diagram? Just we have traced simply how the poles are changing with respect to K value. How the poles are changing with respect to K value. What is one? It is root locus. That's it. Root locus is what? Simply position of roots with respect to disturbance. Is position of roots with respect to various operating conditions. This is going to be called as root locus. Root locus. Yeah. Next heading I am going to take. Next heading. We'll discuss one problem on this one later, because I want to introduce some more mechanical terms to you. Without introducing them, discussing a problem on this, it's not suitable choice, right? So I'm going to take up some more discussion here. Let's say in the next slide. That is combining machines together, or theory. Combining machines theory. Heading I am showing here. Combining machines theory. Why it is needed? Combining machines theory. Combining machines. Why it is needed is just to make the transient stability analysis a bit simple. mathematical transient stability analysis. What we are doing to make that one a bit simple, we are going for the combining machines theory, right? So, okay, right, to reduce the what we call reduce the calculations, or you can say difficulties in transient stability analysis. Transient stability analysis. What we do in this one? Transient stability analysis. What we do in this is simply, for example, in the system, if you have number of machines, let's say we have 100 machines in the system, maybe 100 generators, and some are generators, some are motors, combinations are there. Okay, those machines we might be converting into less number. Maybe 100 machines I will convert into 20. Okay, or else we'll say if you have only 5 machines, those 5 machines I may be converting into 2 machines, or 6 machines I may be converting into 1 machine also sometimes. Okay, so converting number of machines into less number, large number of machines into less number, definitely that will give a feel that number of synchronous generators or synchronous machines in the system has less. Number of synchronous machines in the system has less. Number of swing equations to be solved will be lesser. That will make the calculations as less. Okay, so by that way, by this, a large number of machine system can be converted into less number of machine system, low number of machines system on the paper, not physically, on the paper. Here. Okay, see, actually we have two categories here in the combining machines theory. One category we will say machines are swinging together. Is one category. Other category is machines are not swinging together. Okay, so first category I am taking up now. Machines swinging together. Machines swinging together. Yeah. Okay. So I am showing two synchronous machines here, which are connected to the same bus bar. Generators. Moreover, these are generators. Two synchronous generators. We are connecting to the same bus bar. And this is some mechanical input for first generator, electrical output of first generator. Similarly, second generator, mechanical input, electrical output. The angular momentum of first generator is M. Second generator M. Next one. We have one transmission line wire connected like this. And at the end, you have some infinite bus. Okay, next. This infinite bus machine or infinite machine, rotor angle we are assuming as 0 degree. Infinite machine rotor angle we are assuming as 0 degrees. First generator rotor is making an angle of delta 1 with respect to infinite bus. Second generator making an angle of delta 2 with respect to infinite bus. First generator making an angle of delta 1. Second one is making an angle of delta 2. Next. See, for this machines swinging together, we have different definitions. From textbook to textbook, we have some definitions. And according to the way of understanding, also we can think in different ways. One simple way what the people will say is, if delta 1, delta 2 are equal, then we will say that both machines will swing together. Both machines will swing together. Okay. Delta 1 is equals to delta 2. Then both machines will swing together. Will swing together. Clear? Delta 1 is equals to delta 2. Then both machines will swing together. Yes, go with. Yes. Let's go with. Before discussing exactly what is the meaning of swinging and non-swinging, let me take up one big system. By that I will try to tell you. Okay. I'll come back to this slide. I'll come back to this slide. Between the previous slide and present slide, I have added one thing. Look here, look here. These are two generators, only one generator. One generator connected to one motor, synchronous motor. We have some mechanical input here as a PS1, and we have some mechanical load here as PS2, and this is electrical input PE2. Electrical output here is PE1. PE1. Observe. Listen, all of you. Listen kindly. No, it's not. It's not the thing, Gobi. It's not. Look here, look here. First machine angular momentum M1. Second machine angular momentum is M2. First machine, you know, d omega by dt, PS1 minus PE1. Rate of change in the speed for the first machine is PS1 minus PE1. Second machine, d omega by dt, PE2 minus PS2, right? Second machine, d omega by dt is PE2 minus PS2. Okay, next thing. For example, unfortunately, I had a short circuit fault at this place. Unfortunately, I had a short circuit fault at this place. Listen, just cool, don't try, just listen to my words. Okay? Whatever the things you have in your mind, machines swinging together, not swinging together, and all, just all the things throw away first. All the things throw away, just listen here. Fault occurred at this place. Then definitely this electrical power output will become zero, and electrical power input will become zero for the motor. Means you can see this is only PS1 value which is positive. This is only PS1, right? PE1 is 0, so it is positive. And what is that here? 0 minus PS2. So it is negative. Minus PS2, that is negative. Means tell me, what happened to generator 1 speed? What will happen? What will happen to generator 1 speed? What will happen to generator 1 speed? Increases, right? Generator 1 speed will increase, acceleration. Good. What will happen to the motor speed? Decreases. We have the de-acceleration for the motor. See, whenever you have a short circuit fault here, one machine speed is increasing, other machine speed is decreasing. Means what we can expect the angular difference between these two machines? What we can expect the angular difference between the two machines? Definitely increases, because we have only two machines right now. One machine is increasing its speed like anything, other machine is decreasing its speed like anything. What will happen to the angular gap between these two? Increases. Yes or no? Increases. See, in this particular case, if one machine speed is increasing, other machine speed is decreasing, I will say that these two machines are not swinging together. Machines are not swinging together. Okay? You can write here if you want. So machines are not swinging together. Machines are not swinging together. Machines are not swinging together. I think all of you getting this? Okay, next. One more simple example. One more. One more simple example. Just observe. This is one generator. It's also generator. Generator. Connected to same bus bar. Close. Very close. And it's a line. On this side, we have infinite buses. Infinite bus. Like this way. First machine having mechanical input PS1 and this is having mechanical input as PS2. This is having PE1 and this is PE2. Okay, now very simple. I had a fault on the transmission line at some place. Okay, tell me please. Swing means it's not speed. I'll come to your doubt. Please wait, Dinesh, for some time. Look here. After the fault has been occurred, what will happen to electrical power PE1? 0. Electrical power PE2? Also 0. Then, what will happen to machine 1 speed? Will increase, right? Machine 1 speed will increase. Yes or no? Right. What will happen to machine 2 speed? Also increase. Machine 2 speed will also increase. See, machine 1 is accelerating. Machine 2 is also accelerating. See, with respect to this infinite reference, both machines are increasing its speed, means increasing their angle. Both machines are increasing their angles. Yes or no? As both machines are increasing their angles, we can expect that the variation in the delta with respect to time will be almost same for both machines. Variation in the angle delta with respect to time will be almost same for both these machines. At that time, we can say both these machines are swinging together. In this case. Machines are swinging together. Okay. See, the actual meaning of machines are swinging and not swinging here is, with respect to speed, one thing I discussed in a simple way, with respect to speed. In the other way, what we have to say is, if the angle variation with respect to time, is same for machines, then we can say machines are swinging together. Okay. After the fault has been occurred, output power is 0. The point voltage is 0, right? Yes. Okay, listen here. Somebody asked me, if machines are synchronized, then machines will swing together, right? Synchronization is different. Swinging is different. Please be clear here. Synchronization is different. Swinging is different. For example, in this case, without any fault, I'll say generator and motor are synchronized together. But not swinging together. All of you getting my point? Machines may be synchronized, but not swinging together. Yeah, fine. So next I'll say, let me continue with this one. Again, I will tell you what is it swinging and not swinging as time comes further. Please look here. If delta 1 is equals to delta 2, then both machines will swing together. Next one. See, for example, you take the first machine equivalent circuit. This is the equivalent circuit of machine 1, I can say. Per phase equivalent circuit. Equivalent circuit of machine 2, I can say like this. Per phase equivalent circuit. And then you have some line and then infinite bus. This is a per phase equivalent circuit, right? Per phase equivalent circuit. It is V at an angle 0 degree. This is some voltage E1 at an angle delta 1. This is some voltage E1 at an angle delta 1. EMFs are E1 at an angle delta 1, and then we have E2 at an angle delta 2. Yeah, I will come to your doubt, Govindu. Govindu, don't confuse, just listen. Look here, look here. If you are saying delta 1 equals to delta 2, delta 1 equals to delta 2, what's the meaning of that now? Internal angle of machine 1 and internal angle of machine 2 are equal, right? If delta 1 and delta 2 are equal, can I say there may not be any real power exchange between the two machines? There may not be any real power exchange between the two machines. Yes or no? Tell me please. Yes, we don't have any real power exchange between the two machines. Means I can say before the occurrence of fault or before the occurrence of the disturbance, if you don't have any power exchange between the machines, if you don't have power exchange between the machines, then I can say simply the machines will not swing together, Okay, right. I am writing that statement. If there is no initial power exchange or power exchange in pre-disturbance condition, power exchange in initial condition, then machines will swing together. Machines will swing together. Machines will swing together. Okay, next thing. Only real power we are talking here. Only real power, not with respect to reactive. We are talking about only real power. Real. Next. Listen here. See, for example, in a power plant, I have number of machines, number of generators, maybe number of generators in a power plant. We have number of generating units like this. Number of generating units, and all are connected in parallel. And connected to same bus bar. Kindly observe. All are connected in parallel and connected to same bus bar. Tell me please, can we assume now these machines will swing together? In a power plant, we have number of machines connected together. Can we assume now these machines will swing together? Yes or no? Definitely. What's the reason? Delta may be same for all the machines. That's one reason. Other machine is we may not have any power exchange from one machine to other machine in the initial condition. Okay. So in an assumption, kindly observe here. In an assumption, generally, in a particular power plant, if number of units are connected to the same bus bar, number of generating units running in parallel, irrespective of their ratings, irrespective of their internal impedance value, irrespective of their angular momentum, we will assume that all these units are swinging together. Okay, right. Observe here. In a power plant, already we have written. If number of generating units are connected in parallel, and connected to common bus bar, connected to common bus bar, connected in parallel and connected to common bus bar, then these units are assumed to be in swinging. Assumed to be in swinging. Assumed to be in swinging, irrespective of the ratings, or irrespective of their ratings, power ratings, comma, impedances, comma, moment of inertia, means say angular momentums, etc. Irrespective of these values, we are going to assume that the machines will be in swinging. Yeah, even see, this is not my statement to say, exactly speaking. It's not my statement to say. It is a statement given in Power System Stability by Professor Kimbark. He is the first author of power system stability in the whole world, which I feel. The first author of the power system stability, and all the remaining textbooks what we are having now are extension of that, taken from that, you can say. Okay, so he said clearly that even though initial loading is also unequal, for example, first machine is supplying some power 10 megawatt, second machine is supplying some power, let's say 20 megawatt, but both machines are connected in parallel, connected to same bus bar, then also you can assume that the machines are swinging together for the analysis purpose. Yeah, all of you getting my point? Next thing, let me continue in the other way. Sir, what's the meaning of swing together? Swing together means the angle variation with respect to time. The angle variation with respect to time will be same. The angle variation with respect to time will be same. That's the meaning. d delta by dt value will be same. Next, look here. It's a test for you. It's a small test for you. I'm sure. Yeah. For example, look all of it. It is one generator. It is one more generator connected in parallel, and we have a line connected. G1, G2 generators. Whether these two generators are swinging or not swinging, tell me your answer, please. Tell me, please, whether these two generators are swinging or not swinging. Definitely swinging, right? Why may or may not be? Definitely these two are swinging together. That's it. Next one is two machines. This is a generator, and we have a motor connected to same bus bar, running in parallel, connected to same bus bar. Now tell me whether these two machines are swinging or not swinging. Second case, whether the machines are swinging or not swinging. Definitely not swinging, right? Definitely not swinging. Definitely these are not in swinging. Yes or no? So in this case, machines are in swinging. But in this case, machines are not in swinging. Machines are not in swinging. Machines are not in swinging. Please, can I say, only like machines will swing together? Why? In the sense, we have a power exchange, Pujar. We have a power exchange. You take a fault, one machine speed will increase, other machine speed will decrease, angle variation will increase. d delta by dt's are not same for both machines. That's it. That's what I said just now, Sanjeev. Have you understood this, Sanjeev Api? Have you understood this? Unlike machines. These are unlike machines. Unlike machines means we have a power exchange. Right? So definitely the machines will not swing together. Yeah. Next one. Tell me. Like machines will swing together. That's it. Like machines will swing together. Unlike machines will not swing together. I'll say here, like machines like machines connected to same bus bar. Connected to same bus bar. Same bus bar as well as closely located. Closely located are geographically very close. Geographically very close will swing together. Will swing together. Geographically very close will swing together. I'll tell you the reason why I am saying that geographically very close here. Geographically very close. Induction generator, there is no meaning of row triangle and all. Why you are saying about that, Ashish? I will come to your doubt with reverse. Just look here. Just look here. I have drawn this diagram earlier, right? This one. This one. See, what is the meaning that machines are very closely located? Very closely means geographically very close in the sense we can expect that the interconnection impedance between the machines will be negligibly small. If the interconnection impedance between the machines is negligibly small, then obviously the bus bar voltage, what we have connected bus bar voltage, is nothing but internal voltage of all the machines. Have you understood this now? Tell me. I will repeat the statement. Kindly observe. I will repeat the statement. Kindly observe. If the machines are geographically very close, are connected to the same bus bar, then the interconnection impedance or transfer impedance between the machines can be negligibly small. If the transfer impedance between the machines is negligibly small, then whatever the connected bus bar voltage you have, the same voltage we can say for the induced EMFs or the internal voltage sources voltages will be same as the bus bar voltage. Getting? Yeah. Impedance need not to be same, Ashish. Impedance need not to be same. I will write that statement also for your understanding. Like machines are geographically close. Geographically close and connected to same bus bar. Connected to same bus bar. Same bus bar. Then the transfer impedance between machines may be low, may be very low. Maybe very low. So in that case, internal EMFs of machines will be almost equal to bus bar voltage. Right? Implies machines will have almost same rotor angle at any time. That implies assumed to be swinging together. I said various ways here. Various ways of learning about the swinging. Whichever the way you are comfortable, that you learn, that you study. Okay? Yes, correct. Sunanda, correct. Correct, Sunanda. Sunanda is asking that Sir, there are two motors and one generator connected to same bus bar. For example, here I say I add one more motor here, one more motor. M1, M2. And how will be this M1, M2? M1, M2 will be swinging together. M1, M2 will be swinging together. But this combination will not swing with generator. That's the meaning. Getting? M1, M2 will swing together like machines. Will swing together. Generator will not swing with M1. Will not swing with M1. M1 and M2. Okay. Right. Different ratings also you no need to bother now. But we told irrespective of impedance. Yes, I am confining to the statement only, Saicharan. I'm confining to the statement only. But I'm saying impedances are there. Those are unequal, but low values. What is there in that? Impedance are low values. To tell you about a statement, bus bar voltage and internal voltage will be equal. Bus bar voltage and internal voltage will be equal. Okay, next. Let's consider this plant. We have n units here. N units in the power plant like this. Just observe my words, what I'm saying, N unit power plant. N unit power plant. Having the angular momentums, I'm showing here M1, M2, and so on up to Mn. Angular momentums are M1, M2, and so on up to Mn. Next, one more thing. Mechanical inputs of these units, PS1, PS2, and so on up to PSN. Mechanical inputs are PS1, PS2, PSN. Electrical powers, P1, P2, PEM, like that. Electrical powers are P1, P2, and so on up to PEM. Next, listen. See, what's our aim of discussing all these things? Can you tell me now? Why we are discussing all these things here? What's the aim? What is the exact aim of discussing all these things? Converting these machines into a single machine, right? Converting these machines into a single machine. That's the aim. All of you getting me? I don't know whether you have understood my statement or not. Yes? Tell me please. Yeah. Now, I want to replace these n machines what you have. N machines what you have into a single machine. Into a single machine, bus bar, and then whatever the extension we have further. And this is having some equivalent mechanical input, equivalent electrical output, and this is having some M equivalent. Okay, now listen. The accelerating power, look here. The accelerating power per unit acceleration. The accelerating power per unit acceleration. Acceleration power per unit accelerating power per unit acceleration. What do you mean by that? Accelerating power per unit acceleration means PA by d square delta by dt square. Is it okay? This is the value of accelerating power per unit acceleration, right? PA by d square delta by dt square. I need your response. Nobody is answering. Is it correct or not? What is that value? Anybody tell me please, what is that value? What is that value? That value is nothing but m, right? That is nothing but m. That is nothing but m. Yeah, m. Now, see whether this statement is logical or not, just to check what I am saying. These are statement given in Kimbark textbook only. I am saying from that only. Just tell me, is it logical or not? See, accelerating power per unit acceleration of the equivalent machine, the accelerating power per unit acceleration of the equivalent machine will be equals to sum of the accelerating powers of all the units per unit acceleration respectively. I will write that statement. If machines are swinging together, then the accelerating power per unit acceleration of equivalent machine equal to sum of accelerating power per unit accelerations of the units swinging together. The units swinging together. Clear? Means what we can write from this one? What we can write? M equivalent is nothing but the value M1 plus M2 plus and so on up to Mn. M1 up to Mn. So this is a way of writing the equivalent angular momentum if the machines are swinging together. Okay. Yeah. So have a break for 10 minutes. Sir, there no vector addition. It's not vector addition, Ashish Raj. It's not vector addition. Yeah, have a break for 10 minutes. After break, I will little more discuss about the swinging. Then we go for non-swinging case. Okay, 10 minutes break. I have resumed audio video on screen. Please kindly confirm. Audio video on screen. Is it okay? So let's continue. Let's continue here. See, we have taken a two machine system, something like this, the initial stage, right? Concept of machines swinging together. We have taken a two machine system like this. You show that. Simple derivation kind of thing I am saying. Earlier I said as per definition, m equivalent equals to m1 plus m2 plus and so on up to mn, right? But a simple derivation I am going to get that. Another way you can say. Can you tell me what is swing equation of machine one? Swing equation of machine one. That is m1 into d square delta 1 by dt square is equals to ps1 minus pe1. m1 into d square delta 1 by dt square is equals to ps1 minus pe1. And whereas if you take up second one, swing equation of machine 2, if you take up, that is m2 d square delta 2 by dt square is equals to mechanical ps2, electrical will be pe1. Already you know delta 1 and delta 2 are equal. Already you know delta 1, delta 2 are equal. So after saying that delta 1 and delta 2 are equal, simply I will add these two equations together. Equation 1 you take, equation 2. So add equations 1 and 2. Equation 1 plus equation 2 we are going to. Yeah, please complete it quickly. I will move to next slide. Equation number 1 plus equation number 2 we have to do that. Equation 1 plus equation 2. So we have m1 d square delta 1 by dt square. 1 d square delta 1 by dt square. Yes, we have m2 d square delta 2 by dt square is equals to what you'll have ps1 minus pe1 means you write ps1 plus ps2 one term and you have other term as pe1 plus pe2. ps1 minus pe1 plus ps2 minus pe2. ps1 plus ps2 minus pe1 plus pe2. And already delta 1, delta 2 are equal. So you can say this as m1 plus m2 multiplied with d square delta by dt square simply is equals to ps1 plus ps2 you write as ps equivalent. pe1 plus pe2 you write as pe equivalent. Already m1 plus m2 you can call it as m equivalent. M equivalent. All of you getting it? Simply we have to add up the angular momentums of the machines to get the equivalent angular momentum. Then what is the value of PS equivalent? PS equivalent will be PS1 plus PS2. What is PE equivalent? PE1 plus PE2. Okay. Do it quickly. Take up in the next slide. It's PE2. PS2 minus PE2. Yeah, PE2 yeah. So whatever the two machine system we have right now, this one, two machine system, what we have here right now. Angle we have delta 1 here already. So this we are going to convert into a single machine connected to infinite bus bar. Single machine connected to infinite bus bar. This 0 degree angle. And this is which is said as PS1 plus PS2. And this is PE equivalent, which is PE1 plus PE2. And angle is delta, which is nothing but delta 1 as well as delta 2. Rotor angle will be delta with respect to infinite bus. Either it is delta 1 or delta 2. Equivalent angular momentum, M equivalent, which we said as M1 plus M2. Equivalent angular momentum is M1 plus M equivalent. So I think you are clear now. Can you tell me what is reactance of this machine, equivalent machine? X equivalent is how much? X equivalent, equivalent reactance of this machine, how much? Anybody? X equivalent. Because two machines are in parallel, right? If machines are in parallel, obviously reactances will also be parallel. Then how much will be that number? X1 in parallel with X2. X1 in parallel with X2, not the addition. Not the addition. It is a parallel combination of X1 and X2 in per unit form on the same base. In the per unit form and on the same base. Okay? X1 in parallel with X2. Not by 2, not by 2, Rahul and Imtiaz. It's not by 2. It will be in parallel. X1 in parallel with X2 we have to consider. And similarly, if you are converting this N machine system into a single machine system, you are converting this N machine system into a single machine system. M equivalent already we know M1 plus M2 plus and so on up to Mn. And whereas if you write X equivalent of this one, what you have to say? X1 in parallel with X2 in parallel with and so on. Xn. Whereas M equivalent already we said M1 plus M2 plus and so on. M1. And PS equivalent is summation of all these PS values. PS1, PS2, and so on to PSN. And P equivalent is P1 plus P2 plus and so on to PN we have to say. I think all of you a bit clear about the machines swinging together till now. Machines swinging together till now. Later on, we will take up machines not swinging together. Machines not swinging together. Strictly speaking, listen. Strictly speaking, when exactly the machines will swing together. When exactly the machines will swing together means if the rotors of all the machines are on the same shaft. If the rotors of all the machines, all units, all generating units are on the same shaft, then we can say machines will be swinging together. It won't happen practically speaking. Practically, if you are doing that, you don't have a facility of switching off of one unit, switching on of one unit, transferring power from one unit to other unit. That choice you don't have. Following all of you, right? Fine. So let's take up the next heading now. Machines not swinging together. Not swinging together. Machines not swinging together. Okay, to explain this one, machines not swinging together, I'm considering two big areas. Power system network areas I'm considering. Let us say this. So this is some area we have. Area 1. And this is some other area. I'm calling it is area 2, which you can say sometimes as control area, or you can say coherence area. Okay. Coherent area. Coherent area. What do you mean by coherence? What do you mean by coherence? Coherence means swinging together only again. Swinging together, right? Coherence is nothing but swinging together. Or in unison, also you can say. Machines are swinging together, or in coherence, or in unison. Any statement you can write. I write the previous slide. Machines swinging together. Swinging together can also be called as in unison. Machines are in unison, or you can say in coherence. All these terms will be same. All these terms will be same. In unison or in coherence. Okay, fine. This is one coherent area we have, coherent area. So in which we have number of machines, might be swinging together, And again, this is area one. Here also we have number of machines, might be swinging together. And we are connecting one transmission line wire between these two. For what purpose? For what purpose you are connecting the transmission line wire? Anybody tell me, please? Anybody please tell me. For what purpose you might be connecting the transmission line wire? For power exchange. Maybe we want to transfer some power from area 1 to area 2 or area 2 to area 1, whatever it is. So for power exchange, we are connecting that transmission line. This line is going to be called as generally tie line. This line is going to be called as tie line. See, tie line is nothing but a simple transmission line wire. Which is connecting two big areas of power system network. And one more thing, what you can expect is once after disconnecting this tie line, I feel that the two areas are disconnected. Completely disconnected. That is what we call a preference we should give for this line particularly, right? It's nothing but a transmission line wire only. Same as a power conductor what we have outside, right? But it's connecting to big power system areas. Now, listen. See, this area one what we have, that I converted into a single machine, something like this. It's a area one representation, some mechanical input PS1, and we have some electrical output as PE1, and we have some angular momentum for this area as M1. Angular momentum for this area 1 unit as M1. Similarly, area 2 also, we are going to represent in the similar way. And this is mechanical PS2 input. And this is electrical output PE2. And this is having an angular momentum of M2. Okay. And these two areas are connected together by using a transmission line wire, which we call as tie line artery. So this is the tie line what we are connected earlier. Okay, next thing. Listen all of you. So this machine rotor angle I am considering as delta 1. This machine rotor angle I am considering as delta 2. Yeah, from which area to which area the power is flowing here? We have to assume it actually. We don't know the numbers, right? We don't know delta 1 number and delta 2 number. As you don't know, you can assume in any direction. But you tell me, which direction you want me to assume? Is it from area 1 to area 2 or area 2 to area 1? Let us consider area 1 to area 2. So this is the direction of the power exchange. It is a direction of the power exchange. Okay, next thing. So definitely delta 1 and delta 2 are unequal. Right? As we have power exchange. As there exists a power exchange. Delta 1 and delta 2 are unequal. Yeah, you please tell me now. Listen. Please tell me. Whether these two machines are swinging or not swinging. I need your answer properly. Whether these two machines are swinging together or not swinging together. Tell me. Definitely not swinging together. These machines will not swing together. Okay. I will try to explain you the machines are not swinging together concept in the similar lines. Here. Just observe. Else you write first. That implies machines are not swinging together. Now, how to replace this two machine system which are not swinging together into a single machine? How to convert these two machines not swinging together into a single machine system? That's the thing which we are interested to know now. See, actually, As we are doing transient stability analysis, all of you listen kindly. All of you listen kindly. As we are doing transient stability analysis, our interest is to learn how the delta is changing with respect to time. How the delta is changing with respect to time. That we have to know. Which delta I have to study now? Is it delta 1 or delta 2? Which delta I have to study in the transient stability analysis? Please tell me, which delta I have to study? Is it delta 1 or delta 2? Strictly speaking, it is delta 1 minus delta 2, not 1, Murali Krishna. It is delta 1 minus delta 2. That's the resultant angle, right? That's the resultant angle between the two rotors. That we have to study whenever we have a disturbance. So our swing equation should come in terms of delta 1 minus delta 2. Okay? Yeah. So I can say here, in this case, delta 1 minus delta 2 versus time must be studied in transient stability analysis. The transient stability analysis. Transient stability analysis, you should study delta 1 minus delta 2 versus time. Okay, fine. Next thing. One more thing I am saying you. So how is the required swing equation now? How will be the required swing equation? The form of required swing equation would be M equivalent into d square delta 12 by dt square is equals to PS equivalent minus PE equivalent. M equivalent into d square delta 12 by dt square equals to PS equivalent minus PE equivalent. Whereas the delta 12 is delta 1 minus delta 2. Delta 12 is nothing but what? Delta 1 minus delta 2. Yes. Power flow will occur due to the difference in the swing. Next one. Let's continue now. This is our aim. This is the way how we have to construct the swing equation. That's what our aim. Let us say like this. First, you look from this figure. There is some ambiguity in this figure. Definitely, I will clear that now. There is some ambiguity in this figure. Look here. No loss. Lossless system. Complete system is lossless. Look now. PS1 input. PE1 output. Definitely, PE1 and PS1 are equal without any disturbance. Without any disturbance, I am saying PE1, PS1 both are equal. PE1, PE2 are in opposite, right? PE1, PE2 are in opposite means I can write this PE2 as minus PE1. PE2, you can write it as minus PE1. Is it correct or not? Is it correct or not? Tell me please. PE1, you can write it as minus, PE2, you can write it as minus PE1. And you see, PS2 is nothing but PE2 only. PS2 is nothing but PE2 only. And the PE2 is what? Minus PE1 means, can I write this one minus PS1 here? Minus PS1. All of you getting this? Minus PS2. PS2 equals to minus PS2. So even though I am showing the input, PS2 as an input in this direction, but strictly speaking, it is going to act as a load. It's going to act as a load because we have a power transfer from one to the other. What is the second machine now? Is it strictly a generator or motor now? What is the second machine? Is it strictly generator or motor? Anybody? Is it strictly generator or motor? Motor. But listen now. Motor. But do we have a physical motor there? Physically, do we have a synchronous motor? Physically, do we have a synchronous motor there? No, there is no physical motor. There is no physical motor. Whatever the power system area we have, inside which we have number of synchronous machines, loads, transformers, lines and all, that whole area 2 is taking some power from area 1. So if you look at area 1, and see the area 2 is taking power, right? Area 2 is taking power, means that is acting as motor, and area 1 is supplying power, means it's going to act as generator in this particular state. I think all of you getting the feel of that motor here. Yeah, correct, correct, Alia. Yes. Yeah, let's move ahead. Let's move ahead. Let's write swing equation of and machine 2. Swing equations I will write first. Thereafter, we will think how to get the equation. Area 1. Swing equation. M1 d square delta 1 by dt square equals to PS1 minus PE. M1 d square delta 1 by dt square equals to PS1 minus PE1. Okay, what is the area 2 swing equation? You write in the same way. Don't change. You write in the same way. So M2 d square delta 2 by dt square is equals to PS2 minus PE2. Clear? PS2 minus PE2 we can write. But you have to get this swing equation in terms of delta 1 minus delta 2. Delta 1 minus delta 2. For that purpose, look, for that purpose, first equation what we have, first equation I will rewrite as d square delta 1 by dt square is equals to PS1 minus PE1 by M1. Is it okay? PS1 minus PE1 by M1. And whereas second one, d square delta 2 by dt square, you can write it as PS2 minus PE2 by M2. PS2 minus PE2 by M2. Okay, you call this as equation 1. This as equation 2. And you take equation 1 minus equation 2, you will get it right. Equation 1 minus equation 2, you do, you will get it. No, actually, Sivagopi Raju and Dinesh, listen, please. Listen, all of you. If anybody having a doubt, somebody is asking me, sir, why can't you show area 2 simply as a load? Why you are saying that as a motor? Means simply by disconnecting this tie line, look here, by disconnecting this tie line, if we construct the Thevenin equivalent model for this area 2, Thevenin equivalent model with respect to area 2, what you get? What you get with respect to area 2? Anybody tell me, please? With respect to the area 2 terminals, if you convert that area 2 into its equivalent model, what you are going to get? A voltage source in series with reactance, right? A voltage source in series with reactance. That's it. So it will be acting as a motor definitely. It's a voltage source, but it's going to take the power from area 1, right? It's going to take the power from area 1. So definitely you should make it as a motor in the equivalent circuit. Simple. Okay. Yeah, let's continue. Let's continue. Equation 1 minus equation 2, we have to exercise now. Equation number 1 minus equation number 2, we have to take. So that is d square delta 1 by dt square. D square delta 2 by dt square here is equals to, observe, PS1 minus PE1 by M1. Okay, minus PS2 minus PE2 by M2. Minus PS2 minus PE2 by M2. And if you rewrite this, d square by dt square, delta 1 minus delta 2 equals to, yeah, take this LCM, M1, M2. And here you have M2 PS1 minus M2 PE1 minus M1 PS2 plus M1 PE2. M1 PE2. Like this, we are going to it. I think all of you getting this? Just do it quickly. Yeah. So whatever this M1, M2 you have, that you take the LHS side, M1, M2, and this I write d square delta 1 2 by dt square. D square delta 1 2 by dt square. Next thing. this one. I'll take PS terms one side. M2 PS1 minus M1 PS2 minus M1 PS2 minus M2 PE1 minus M1 PE2. M2 PE1 minus M1 PE2. Okay. Next. Next. See, is it in the required form of swing equation? Anybody? Is it in the form of this required swing equation? M equivalent into d square delta 1 2 by dt square equals to PS equivalent minus P equivalent. Is it in that form? Is the swing equation what you have derived till now? Is it in that required form? Yes or no? No, it's not in that form, right? No, it's not in that form. Why in the sense? Here we have M square, right? Here we have M square, but we need only M units to follow. What you have to do? What you have to do? What you have to do to get this in the proper form of swing equation? It's not near M square you have, right, Ashish? It's M square, yeah. What you have to do? See, actually, already we said PS2 value here. PS2 value is equals to minus PS1. PE2 value minus PE1. So you can keep that here. So in place of PS2, we keep minus PS1. In case of PE2, we keep minus PE1, and we can simplify it. Let me keep that. So PS2 you replace with minus PS1. PE2 you replace with minus PE. So I'll move in the next slide to take up this expansion further. M1 M2 d square delta 1 2 by dt square is equals to, you can get M2 PS1 plus M1 PS1. Minus will be cancelled there. Minus of, observe, M2 PE1 plus M1 PE. M2 PE1 plus M1 PE1. 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 So if you take that M1 plus M2 common, M1 plus M2 common, you will get here PS1 minus PE1. And you take that M1 plus M2 to the other side, M2 by M1 plus M2 multiplied with d square delta 1 2 by dt square is equals to PS1 minus PE1. PS1 minus PE1. That we have replaced just now, Shreya. Shreya, that's what we have replaced just now. What is M1 equation? Please do it properly. Please do it properly. Take care of this replacements, what I said properly. In place of PS2, you keep minus PS1. Minus will be cancelled out. You get M1 PS1. In place of PE2, you keep minus PE1. Minus will be cancelled. M1 PE1 again. See, this is nothing but M equivalent value. If two machines are not swinging together, that's the M equivalent value. And it is PS equivalent value. And this is nothing but PE equivalent value. PE equivalent value. All of you getting? Yeah. So now I will take up this two machine system with what we have started this one. This is the two machine system with what we have started actually. So let's take here. This is a two machine system we have taken up. Simple, very simple thing. Very simple thing. This two machine system, we are going to convert into a single machine. This two machine system we are converting into single machine. This is that single machine. Listen carefully. What is input now? This PS equivalent is what? PS1 only. What is PE equivalent? That is nothing but PE1. PS equivalent is PS1. PE equivalent is PE1. What is M equivalent value? M equivalent value. M1, M2 by M1 plus M2. M1, M2 by M1 plus M2. That's the M equivalent value. And next, what you have to draw? After this, what you have to draw? Line. What's the angle of this one? What's the angle of this one? Delta 1, 2, right? Which is delta 1 minus delta 2. How's our PE, PS equivalent? Okay. Go to the equation and compare. How in the sense, that's what I explained till now, right? So here M1, M2 are like parallel combination. That's your convention and your assumption what you make. That's your wish. Yeah, look here, please. And here, I'll say from this point, you have a line, whatever the tie line you have shown there. Line. And what you have at the end? Anybody tell me? What you have at the end? Anybody tell me? Anybody? This we are going to say as infinite bus. That we are going to say as infinite bus. And this is having an angle of 0 degrees. That is the infinite bus, and that is having an angle of 0 degrees. It's simply what you have done simply here is whatever the angular momentum M2 we have for second machine, M2 angular momentum what we have for second machine, that we have superimposed onto first machine. That we have superimposed onto first machine, and we got that M equivalent value like M1, M2 by M1 plus M2. Simple. And what is the angular momentum of this one? Anybody tell me? What is the angular momentum of infinite bus system? That will be infinite, right? This machine angular momentum will be infinite. Simply the second machine angular momentum we superimposed onto first machine, and we got the resultant like M1, M2 by M1 plus M2 by making the other machine as infinite machine. Infinite machine. Clear? Next thing. So can we apply this non-swinging concept for any number of machines we have? Can we apply this concept of non-swinging for any number of machines? May not be. May not be. Why it is so means I will tell you. With a simple example, I will try to tell you. Look here. For example, we have 3 machines here connected by some transmission line wires, long transmission line wires, you say. Because if the lines of shorter length, you might be assuming that machines may be in swinging. Machines may be in swinging. So I am saying these are of longer lengths. First machine angle delta 1, second machine angle delta 2, third machine angle is delta 3. And angular momentums M1, M2, M3, and all these 3 angles are unequal. These 3 angles are unequal. Delta 1 not equals to delta 2 not equals to delta 3. Simple. Now, how is M1 and M2 machines? How will be that M1, M2 machines? Swinging or not swinging? M1, M2 machines not swinging together. M1, M2 machines are not swinging together. At that case, what you do is we convert that second machine into infinite bus, means 0 degree angle and say, and the resultant angle of this machine will come to be delta 1 minus delta 2. What is M equivalent of this one? It is M1, M2 by M1 plus M2. M1, M2 by M1 plus M2. Okay, but third machine we keep as it is. Third machine we keep as it is, delta 3 angle. Third machine we are keeping as it is, that is delta 3 angle. All of you getting this one? All of you getting this? Please tell me. I need your response. Second machine we superimposed onto first machine, not swinging together. M equivalent value comes to be M1, M2 by M1 plus M2. The angle of this machine is delta 1 minus delta 2. Other machine angle we made 0. Other machine angle we made 0. Okay, now simple. Superimpose a machine 3 onto the machine 1. Superimpose a machine 3 onto the machine 1. What you have to do? I'll show here. This is that single machine what you are asking, and this is infinite bus, 0 degree. And this third machine also you superimposed onto first one. So this angle also comes to be 0 degree. this. And this angle will come delta 1 minus delta 2 minus delta 3. That angle will come to be delta 1 minus delta 2 minus delta 3. What is M equivalent of this one? Let us say, listen. First one is M equivalent 1, you assume. Now it is M equivalent 2. What is M equivalent 2? M equivalent 1 into M3 by M equivalent 1 plus M3. M equivalent 1 into M3 by M equivalent 1 plus M3. Reactances you keep at that location only. Vaishnavi, if the machine 2 is having some reactance, you keep some reactance and infinite bus. Machine 3 is having some reactance, keep some reactance and the infinite bus. Look here, all of you. Look here. So in this case, if you want, you can say 1 by M equivalent value. 1 by M equivalent value is nothing but 1 by M1 plus 1 by M2 plus 1 by M3. Is it correct or not? From this combination, you can write as 1 by M equivalent equals to 1 by M1 plus 1 by M2 plus 1 by M3. You should not say machines are in parallel. You should not say M values are in parallel. As we have resistors in parallel, 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3. You should not say M's are in parallel here. What you can say is, it is almost looking as same in the manner of resistors connected in parallel. That you can say, but you should not say M's are in parallel here. You should not say M's are in parallel. Clear? Next thing. Listen. We converted this. See, whatever the final result you got here, what you got, is it looking as a original system or not? That's the question. Is it looking as a original system or not? See, anywhere at any time, maybe in this subject or any other subject, if you say one system as an equivalent to the other, one system is an equivalent to the other, definitely properties must be same. Properties must be same. For example, you see in our original system, this is our original system, right? This is our original system. How is delta 2 and delta 3? Delta 2 and delta 3 unequal. Definitely we have some power flow in this line. Delta 2 and delta 3 unequal. Definitely we have some power flow in this line. But what you are saying here, both are 0 degrees, right? Both are 0 degrees means you don't have power in this one. In the original case, we are saying there is a power flow between bus 2 and bus 3, but after doing the conversion, we are saying that there is no power between bus 2 and bus 3. That's the wrong. That's the wrong. All of you getting my words? All of you getting my words? Please tell me. So, not swinging together concept generally used if you have two machines in the system. If you have number of machines in the system, not swinging together, converting them into a single machine. Listen, please. Listen to my words. If you have number of machines in the system, converting them into a single machine by using this formula, this type of formula may not be preferable. But this formula is not valid to convert. But we have some techniques to convert if the machines are not swinging together into a single machine, even in the multi-machine system also. This formula is not suitable. That's what I'm saying. I'm not saying that we should not convert or we can't convert. This formula is not suitable. That's the thing I'm saying. So that's why most of the times in the examination, if the machines are not swinging together, they used to ask the question only based on two machines. Okay, fine. Let's move ahead. I will ask one silly question to you. Very, very silly question. Just observe what I'm giving here. This is one generator having an angular momentum M1 connected to infinite bus bar. And how much is the angular momentum of infinite bus bar? Infinite. The angular momentum of infinite bus bar is infinite. Yes. Tell me, please. Tell me. It's a machine 1 you feel, and it's a machine 2. Whether these two machines are swinging or not swinging. whether these two machines are swinging or not swinging. Tell me please. Swinging or not swinging? Again somebody is saying swinging. Gopiraj, what happened? What you have learned, Gopiraj? Swinging or not swinging? Not swinging. Why? Why? We have a power exchange, right? Whether these are in close or not close, why you are bothering about it now? Why you are bothering that whether the machines are close or not close? Doesn't matter. We have a power exchange. So machines will not swing together. Machines will not swing together. Yes or no? Right. So machine one are together. Machine two will not swing together. But those are in synchronism. Under steady state, these two machines will be in synchronism. Okay, if the machines are not swinging together, what is the M equivalent? How to calculate M equivalent? 1 by M equivalent equals to 1 by M1 plus 1 by M2. 1 by M equivalent equals to 1 by M1 plus 1 by M2. 1 by M1 you have, 1 by M2 means 1 by infinite. So this value was 1 by M1 only. So how much is the value of M equivalent here? That is nothing but the value of M. M equivalent is nothing but the value of M1. All of you getting this? Okay. How power exchange is occurring means you are connecting that generator to infinite bus. So we have a power supply from generator to infinite bus, right? We have a power supply from this generator to infinite bus. That's it. Power exchange is there. You write if you want. Okay, done. So in my view, or in your view also now from this point, if you have a single machine connected to infinite bus bar, single machine connected to infinite bus bar, what is the M equivalent of that system? What's the M equivalent of that system? That is nothing but the M value of the single machine what you have. That's nothing but the M value of the single machine what you have. Clear? I'll take one problem on this concept. I'll take one problem on this concept. Kindly observe. So in the additional questions PDF 5, it is question number 10. Question number 10 in the additional questions PDF 5. Go through this. Check that now. Check this. So consider the following figure in which station A and station B are very closely located. Station A and station B are very closely located. A and B here, very closely located and connected to a bus bar, extended by a tie line. Extended by a tie line. Tie line means it's a very long length of transmission line. At the end of this tie line, station C is connected. Station C is connected. Each unit angular momentum is given in the figure m, 2m, 2m, m, 2m, 2m like this. If the equivalent angular momentum of SMIB is k into m, equivalent angular momentum of SMIB is k into m, then the value of k is how much? Then the value of k is how much? Yeah, kindly observe. Solution. So this is that system given station A, station B, station C, something like this. Listen to my words. Listen to my words. How will be these three machines? Station A, three machines, swinging or not swinging? These three. Definitely swinging, right? Swinging. How much is the equivalent? Means what is the value of MA? MA is equals to M plus M plus M, 3M. MA equals to 3M. Getting? Good. And how these two machines will be? Stationary machines. How these two machines will be? Swinging or not swinging? Swinging. What is MB? 2m plus 2m, that is 4m. MB, 2m plus 2m, that is 4m. What about station A, station B? What about station A, station B? Swinging or not swinging? Station A, station B, swinging or not swinging? Swinging only. Station A, station B will be again swinging. Why? Because machines are stations are very, very close. As the stations are very, very close. Stations are very, very close. It's a MA, EM, is a MB, 4M. These two will be swinging together. These two will be swinging together. And that M equivalent of this is M equivalent 1, right? 3M plus 4M, that's 7. 7. What about station C units here? What about station C 4 units? Swinging or not swinging? Swinging. How much is this MC? M plus M, 2M plus 4M. That means it will be 6M event. 6M. So this is MC. We have a tie line here connected. And at the end of the tie line, we have one more station with the MC reactance. Sorry, MC momentum. 6M. 6M. How these two will be? Tell me. How these two will be? Swinging or not swinging? 7M and 6M. Swinging or not swinging? Not swinging. What's the reason? Because these are connected by a tie line. Connected by a tie line. So definitely there is a power exchange between these two. That's why these two will not swing together. Will not swing together. Swing together. So finally, I can say M equivalent of this whole system. M equivalent of this whole system will be M equivalent of this whole system will be 7M into 6M by 7M plus 6M. 7M plus 6M. How much is that? Tell me please, what is that? 3.23M. 3.23M. Already he said equivalent angular momentum is a K into M. Na? So the value of K is nothing but 3.23. Value of K is nothing but 3.23. Yeah. So this is a little about angular momentum which we have discussed today. And we have to introduce one more term now that is called as inertia constant. Inertia constant, which is going to give a relationship between what we call electrical and mechanical terms and all, right? So that term we are going to start now, inertia constant, which is very important for the examination, right? Inertia constant. Inertia constant. Just we'll take up the definition of this inertia constant. I'm sorry. So I resumed audio, video, and screen. Is it okay? Simple. Look here, look here. Inertia constant, generally we will be giving this notation as h here. Inertia constant we are going to give with a notation h. Just I will tell you definition of this one. It is, look here, it is the amount of kinetic energy stored in the rotor at synchronous speed rotation. At synchronous speed rotation. So it is the amount of kinetic energy stored in the rotor at synchronous speed rotation to produce 1 MVA electrical output from the stator. 1 MVA electrical output from the stator. Clear? Amount of kinetic energy stored in the rotor at synchronous speed rotation to produce 1 MVA electrical power output from the stator. Yeah. Next, look here. I will take up one small numerical problem to explain about this H value and all. Okay. So I will move in the next slide. For example, a generator, synchronous generator has ratings. 50 MVA. Okay. J, moment of inertia we have said earlier, right? 8,000 kilogram meter square. 8,000 kilogram meter square is a moment of inertia, and it's a 4-pole machine. 50 hertz frequency. 50 hertz frequency. Yeah. Tell me in your way, after looking at these numbers, if it's a rotating body, what is the amount of kinetic energy stored in the rotating body? What is the amount of kinetic energy stored in the rotating body? Kinetic energy stored in the rotor. Formula half J omega square. Kinetic energy in the sense, is it electrical or mechanical? Kinetic energy means, is it electrical or mechanical? Mechanical. It's mechanical means it's a omega s m we have to call. Omega s m means omega s mechanical we have to substitute here, not electrical. Omega s mechanical we have to substitute, right? Kinetic energy stored in the rotor at synchronous speed rotation. Synchronous speed of rotation. Okay. So what is it? Omega s m? It is nothing but 2 pi ns by 60. 2 pi ns by 60. What is it ns? 2 pi ns will be 1500 rpm by 60. If you want to write here, synchronous speed ns equals to 120 f by number of poles. 120 f by number of poles. 120 into f is 15. How many number of poles you have? 4. So it will come to be 1500 rpm. 1500 rpm. So this is the value of omega s. Now you substitute these values into that kinetic energy, you will get that value in terms of joules. Kinetic energy stored in the rotor, you are going to get in terms of joules. So kinetic energy is equals to half J 8,000 into omega s 2 pi ns by 60 whole square. 2 pi ns by 60 whole square. It will be in terms of joules. Get this number, please. Get this number. Anybody? How much is this value? How much is this value? You tell in terms of 10 power 6. You tell this in terms of 10 power 6 joules. 10 power 6 joules. Please kindly check it again, Abhijit. Kindly cross check it. 98.96 maybe the suitable one, I think so. 98.96 into 10 power 6. You can write it as 98.96 megajoule. Okay, I need a simple answer from you. Listen. I need a simple answer from you. This 98.96 megajoules is a kinetic energy stored in the rotor for what? For what? Is a kinetic energy stored in the rotor at synchronous speed. For what? To produce a rated output. To produce the rated output from the stator. What is the rated output from the stator? 50 MVA. Means it is a kinetic energy stored in the rotor to produce rated electrical output. Means 50 MVA output from stator. Output from the stator. Okay, but what is the H value we said? What is the inertia constant we said? Inertia constant. It is a kinetic energy to produce 1 MVA, right? It's a kinetic energy to produce 1 MVA. Means for 1 MVA, how much is that number? 98.96 by 50. 98.96 by 50 means inertia constant H is nothing but kinetic energy stored in the rotor at synchronous speed. Stored in the rotor at synchronous speed by we have to say rating of machine in MVA. Rating of machine in MVA. Or rating of machine, that's it. Rating of machine. So therefore I can write the next slide. H value is 98.96 megajoules in the numerator by 50 MVA in the denominator. 50 MVA in the denominator. And that megajoule and MVA, you keep as it is. Okay, you find out this number, this ratio, how much? This ratio 1.9792. 1.9792. What will be the units of this one? What will be the units of H? Megajoule by MVA will be the units of H. Megajoule by MVA will be the units of H. I think all of you getting this. So you write separately if you want. Units of H inertia constant is megajoule by MVA. Yells. You can write this simply as joule by volt ampere also. Mega you can cancel it. Mega you can cancel it, and you can write that as megajoule. So joule by MVA simply. Yells. That megajoule what we have, you can write it as megawatt second by MVA. You can write that megajoule as megawatt second. Of course, you have MVA. And what is it? Megawatt by MVA? Megawatt by MVA, you can write as per unit megawatt. Per unit megawatt second. Megawatt by MVA, you can write it as per unit megawatt second. Else, you can write this simply seconds also. Any unit you can use among these things. Kilojoule by kVA is also unit. Kilojoule by kVA also one of the unit. And megawatt second by MVA. Or else per unit megawatt second. Or else simply seconds also we can use. So we will stop at this point today. In tomorrow class, we will continue with this H, and we'll do some number of problems in this one. After that, we'll take up exact transient stability analysis. Exact transient stability analysis. Right. If you have any doubts, you can ask me. I will make all the hands low. Please raise your hands now. Vashri.
Sir, 1 not 10, I think 110 or 100, I think, sir. Page here. It's unsticky.
Right?
Oh no, sir.
110.
Sir, that lagging power you taken, sir. the diagram.
lagging power. So,
సార్ మనం లాగింగ్ తీసుకున్నప్పుడు ఇది కూడా కాదు సార్, దాన్ని ముందు నేను నా డౌట్ అయితే నేను చెప్తాను. అయితే లాగింగ్ పవర్ తీసుకున్నప్పుడు లాగింగ్ అంటే నెగటివ్ కదా సార్?
negative. Generally, real power will flow from higher voltage angle to lower voltage angle.
సార్ నేను ల్యాబ్ లో చేసినప్పుడు మా సార్ ఉండి ఏమన్నారంటే, లీడింగ్ లో ఉన్నప్పుడు అంటే ఆపోజిట్ తీసుకోవాలి అని చెప్పారు సార్. లీడింగ్ లో ఉంటే మనం ప్లస్ అనుకుంటాం కానీ అది మైనస్ అని చేయాలి అన్నారు. అయితే నెగటివ్ లో తీసుకుంటామా లేకపోతే పాజిటివ్ లో
Lagging
తీసుకుంటామా
అన్నప్పుడు negative గా తీసుకుంటాం. That depends upon your reference, Vishnu. That depends upon your reference, how you are considering it.
అంటే లీడింగ్ లో ఉంటే నెగటివ్ తీసుకోవాలి, లాగింగ్ లో ఉంటే ప్లస్ తీసుకోవాలని చెప్పారు
just
సార్.
listen,
అట్లా
just
అనేసి నేను అంటున్నాను.
Just listen.
ఇంకా చెప్పండి సార్.
Two buses here. Only two buses. Bus 1 voltage 1 at an angle minus 80 degree per unit. Bus 2 voltage 1 at an angle minus 60 degree, which is in leading and which is in lagging.
60 is leading, 80 is lagging, sir.
Then what's your doubt? You are clear, right?
Yes, sir. But leading, lagging,
V2 leads V1 by 20 degree. Correct or not?
Yes, sir.
Else V1 lags V2 by 20 degree.
Okay, sir.
For example, if this is some V3 bus, 1 at an angle 0 degree, V4 bus, 1 at an angle 30 degrees. Tell me, in this case,
30 is leading.
Means which you tell in statement.
V4 is
leads V3 by
30
degrees. Else, what you can say? V3
leads lags V4 by 30 degrees.
30 degrees. The same diagram what we have means single line model. You can redraw like this also, right? V3, V4. V4 1 at an angle 0. V3 1 at an angle minus 30. That's also correct, right?
Yes, sir.
If you have only two buses like this, if you have other buses also, then you should not change your reference. Even if you are changing your reference, we should alter the all voltages. Means all angles you have to modify.
Okay, sir.
See, very simple, Yugashri. Once if you change your reference position or reference angle, definitely all the bus voltage angles is going to be modified. Not only bus voltage angle, current angle is also going to be modified. Okay, only sir. One thing is that power is not going to be changed. Real power.
Okay, sir.
Real power value, reactive power value will be remain same. Remain okay. Same direction, remain same value and all. If you change your reference, angles of all the voltages in the system will be changed. As well as the angles of all the currents in the system also going to be changed. But powers will be remain same.
Okay, sir. Sir, swinging ante oscillator movement laga.
You can take it as oscillator movement.
ఓకే సార్. అంటే ఒక దగ్గర నుంచి ఇంకొక దగ్గరికి వెళ్ళినాక మళ్ళీ బ్యాక్ రావడమే స్వింగింగ్. ఓకే. అంటే ఇప్పుడు సార్ ఇంకొక దాంట్లో ఇంతకు ముందుకు బస్ చూపించారు కదా సార్. ఇంకా 150 3 buses. No sir.
With this.
ఇక్కడ సార్ ఇక్కడ Δ1 మైనస్ Δ2 కి కూడా 3 బసెస్ ఉన్నాయి కదా సార్. ఇక్కడ మళ్ళీ మైనస్ Δ3 అని ఇక్కడ కింద తీసుకున్నాం కదా, సేమ్ డయాగ్రామ్ లో ఉంది కదా సార్. అంటే ఇక్కడ
3 buses only you have here also.
ఇక్కడ ఎలా తీసుకున్నా నాకు అర్థం కాలేదు సార్. Δ1 మైనస్ సార్ ఇక్కడ Δ1 మైనస్ Δ2 తీసుకున్నారు కదా సార్ 3 బసెస్ ఉన్నప్పుడు మైనస్ Δ3 ఇంకా యాడ్ చేయలేదు కదా సార్ ఇక్కడేమో Δ3 యాడ్ చేశారు కదా సార్.
This is number one. This is first one. Okay.
Yes, sir.
It is second one. This is third one.
అంటే మీరు Δ1 Δ2 Δ3 ఎలా తీసుకున్నారు సార్ నాకు అక్కడ అర్థం కాలేదు.
Which one? Which diagram?
థర్డ్ డయాగ్రామ్.
Already we have Δ1 minus Δ2.
Yes, sir.
That is the resultant angle of this generator. And whenever we are superimposing third one onto this, resultant angle is what now? Δ1 minus Δ2 minus Δ3, right?
Yes, sir.
That's it. You assume, if you have any doubt, university, you assume this is Δ1 to some value.
Okay.
And then what is the angle of this one after superimposing third one onto it? Δ1 to minus Δ3, right?
Yes, sir.
Then it will be Δ1 minus Δ2 minus Δ3.
సార్ ఇక్కడ Δ3 ఉంది కదా సార్ అక్కడ మనం సోర్స్ తీసుకున్నాం ఇక్కడనేమో 0 అంటే గ్రౌండ్ కి ఇచ్చాం కదా సార్ అక్కడ.
Yes. After superimposing one machine onto the other machine, this will be converted into infinite bus, right? Not ground, infinite bus.
ఓకే ఓకే సార్ అండర్స్టూడ్.
It's infinite bus, not ground.
సార్ లాస్ట్ ప్రాబ్లమ్ దట్ K is equals to 98.69 సార్ 96 కాదు.
Okay, whatever.
Okay,
Value
H is equals to 169 1.9738.
Okay. 98.6. Okay, any other doubt you have, Yogeshri?
Oh no sir.
Vaishnavi.
హలో సార్.
Tell me, Vaishnavi.
సార్ ఇప్పుడు మనము డాంపింగ్ అనేది ట్రాన్సియంట్ స్టెబిలిటీలో కన్సిడర్ చేయట్లేదు, స్టడీ స్టేట్ స్టెబిలిటీలో కన్సిడర్ చేస్తున్నాం కదా సార్. రీజన్ ఏంటి సార్?
Not reason, nothing. If you don't consider damping, your water will not become static with respect to infinite bus.
ఓకే సార్.
If you have an undamped system, if you give some disturbance in the undamped system, how will be the oscillations made by that one? Will it die out or continue to oscillate?
Will it oscillate only, sir?
Oscillate. So in the steady state stability or transient stability, whatever may be the stability analysis you do, if you don't consider the damping, you will get the oscillations continued.
Yes, sir.
Okay?
Yes.
Steady state stability we have considered, this year we have not considered, that's not the thing.
Okay, sir. కానీ మనకి డాంపింగ్స్ అనేది
One more thing. We are neglecting it, but system is not neglecting that, right?
అదే సార్, అంటే ఇప్పుడు అది థియరిటికల్ గానే మనం క్యాలిక్యులేట్ చేస్తున్నాం.
Practically system will have its own damping. It will try to make the oscillations less as time progresses, and finally the angle will become constant if the system is stable.
ఓకే సార్.
Okay.
సార్ మరి ఇంకొకటి, ఇప్పుడు 2 మిషన్స్ ఆర్ ఇన్ స్వింగింగ్ అంటే చేంజింగ్ రోటర్ యాంగిల్ విత్ రెస్పెక్ట్ టు టైం అనేది రెండు కాన్స్టెంట్ గా ఉంటాయి.
ఈక్వల్
అంటే ఉండడం వల్ల యూస్ ఏంటి సార్? అది అర్థం అవ్వట్లేదు సార్.
If it is like that, you can replace the 2 machines with single machine only, right?
అంటే హౌ సార్? మ్యాథమెటికల్ గా మనం ప్రూవ్ చేసాం సార్, కానీ ప్రాక్టికల్ గా ఎట్లా అని అర్థం అవ్వట్లేదు.
See, for example, it is one country. Okay.
Okay.
In this country, people are having 100 power plants. Okay.
Okay.
Each plant has 4 units. Okay. What are the total number of generating units now?
400 units.
Means if you want to do transient stability analysis on this system, on how many units you have to do the transient stability analysis?
And 400 units.
400 units, which is very laborious.
Yes, sir.
then you try to replace each plant as a single unit.
ఓకే సార్.
Physical units are 4, that's okay. I am not disturbing the physical system.
ఓకే
But
సార్.
theoretically on the paper, if you have one power plant consisting of number of units, you replace whole units with a single unit by using that equivalent, M equivalent equals to M1 plus M2 and so on up to Mn.
ఓకే సార్.
After doing that, how many units you get in this one?
ఓన్లీ 1 యూనిట్ 1 అనాలిసిస్ ఈస్ ఇనఫ్ సార్.
100 you get. One analysis. You have not
Sir?
understood what I said.
yes,
100
ఇక్కడ
100
400
power-
యూనిట్స్ వరకు అర్థమైంది సార్. తర్వాత చెప్పండి.
400 units we have. So doing the stability analysis on these 400 units is very laborious.
ఎస్ సార్.
That's why what I am saying to you is, you try to replace each power plant with a single unit by using the combining machines theory.
ఓకే సార్.
Okay, how many power plants you have?
సార్
How many power plants you have?
we have initially 100 power plants sir.
100 power plants only you have. But
Yes.
each power plant is having 4 units. Na?
yes sir.
Those 4 units of each plant convert into a single unit.
ఓకే సార్.
Then how many
100
units we get in the resultant 100?
100 sir. yes sir.
Doing stability analysis on those 100 units will be easy compared to this 400 units.
yes sir.
There we are going to get some help with respect to combining machines theory.
okay sir.
Okay, again in these 100 power plants, if some power plants are very closely located, nearby, just nearby,
yes sir.
right? At the time, those power plants you can combine and you take it into a single machine, if possible. By that time, again, number of units will be little decreased.
okay sir. no, no, sir.
So by that the analysis will become simple.
okay sir. Sir, ఇంకొకటి 125 పేజ్ నెంబర్ సార్. సార్ ఇక్కడ ఈ ఒమేగా డెల్టా ఈజ్ ఈక్వల్ టు రూట్ ఆఫ్ కే బై ఎం అని అది ఎలా చెప్పాను సార్? అంటే అక్కడ యూనిట్
Imaginary part.
స్టేబుల్
Imaginary part. Imaginary part of a rotor. Sorry, root.
అంటే అది
These are the roots, complex conjugate roots, right?
yes
What is the imaginary part of that? Square root of k by m minus d by 2m whole square. That itself is omega.
అంటే స్టేబుల్ రీజియన్ ది ఒకటే 2 పోల్స్
We have
స్టేబుల్.
considered only for stable region.
ఓకే సార్.
Consider it on a stable system. Right?
ఓకే సార్.
If it is an unstable system, there is no meaning to say frequency of oscillations.
ఓకే సార్. అదే సార్ అంటే కన్ఫర్మేషన్ కోసం.
Yeah.
ఓకే సార్. సార్ మరి ట్రాన్స్ఫర్ ఇంపిడెన్స్ అని చెప్పారు కదా సార్ ఒక పాయింట్ చెప్పేటప్పుడు. ట్రాన్స్ఫర్ ఇంపిడెన్స్ అంటే ఈక్వివలెంట్ ఇంపిడెన్స్ అనేనా సార్?
That is the equivalent impedance between two sources.
ఓకే సార్.
Okay.
ఓకే సార్. ఓకే సార్. క్లియర్.
That's it.
దట్స్ ఇట్.
Proceed.
Hello, sir.
Tell me also.
Sir, in 130F, sir.
Okay.
Sir, అక్కడ రియల్ పవర్ 0 అనే కాన్సెప్ట్ ఇంకొక దీంట్లో.
No, if delta 1 equals to delta 2, you write the power exchange equation between these two. What is power exchange equation? E1 E2 by x1 plus x2 into sine of delta 1 minus delta 2.
ఓకే 0 అయిపోతుంది.
Delta 1 equals delta 2, there is no real power exchange.
ఎస్ సార్. అప్పుడు స్వింగింగ్ లో ఉన్నాయని చెప్తామా సార్
Yes.
మనము? ఓకే సార్. ఇన్ 129F సార్ ఒక క్వశ్చన్, జనరేటర్ మోటార్ ఇచ్చి అది స్వింగింగ్ లో లేవు, ఒక మోటరే తీసుకున్నప్పుడు సార్.
Then also those who are not in swinging, correct only.
సార్ అదే సార్, నాకు అది అర్థం కావడం లేదు సార్. ఇప్పుడు పైన 2 జనరేటర్స్ కి బస్ బార్ యొక్క వోల్టేజ్ వస్తుంది కాబట్టి సేమ్ యాంగిల్ వస్తుంది, అప్పుడు 0 అయింది సార్.
But here you have angular difference between generator.
హలో సార్.
Here you have an angular difference between generator and motor.
ఓకే సార్.
Then we have a power exchange between them.
ఒకవేళ బస్ బార్ ఉన్నా కూడా అవి ఇన్ఫైనైట్ బస్ బార్ ఉన్నా కూడా ఎక్స్చేంజ్ లో ఉంటాయి.
Whatever it is, definitely you have if you have generator and motor, definitely there is a exchange of power.
ఓకే సార్.
Angles may not be equal. We have an angular difference.
ఓకే.
Okay.
అప్పుడు బస్ బార్ వోల్టేజ్ రాదా సార్ రెండిటికి?
No, it may not come, right? Because angle difference is there. You
ఓకే.
don't get bus bar voltage at that time.
ఓకే సార్. సార్ మళ్ళీ ఫాల్ట్ అక్కర్ అయితుంది. అది చెప్పారు కదండీ సార్ స్వింగింగ్
For example, you take fault at this place.
యెస్ సార్. అదర్థం.
Generator is delivering 0 power output,
యెస్ సార్.
but we have some mechanical input. So generator speed will increase.
యెస్ సార్.
And but as we have fault here, this motor is not taking any real power input.
యెస్ సార్.
As it is not drawing any real power input, but we have a load on the shaft.
యెస్ సార్.
So this speed will decrease, right?
ది స్పీడ్ విల్ డిక్రీజ్. యెస్ సార్.
Then one machine is moving in one direction, other machine is moving in the other direction. The angular difference will increase.
ది స్పీడ్ ఓకే సార్. గాట్ ఇట్ సార్.
Okay?
గాట్ ఇట్ సార్.
These are some techniques to understand exactly what is swinging and all.
ఓకే
That's
సార్.
it.
ఇక్కడ కింద 2 మోటార్స్ ఉన్నాయి కాబట్టి సేమ్ యాంగిల్ డిఫరెన్స్ ఉంటుందని మనం తీసుకుంటామా సార్ అక్కడ?
Like machines, no, like machines, you will assume swinging together.
ఓకే సార్. ఓకే 134 F సార్. సార్ పర్ యూనిట్ యాక్సిలరేషన్ అది అసలు అర్థం కాలేదు సార్ ఫార్ములా.
Accelerating power per unit acceleration.
yes సార్. ఇప్పుడు యాక్సిలరేటింగ్ పవర్
Listen, what is accelerating power formula? PA.
PA సార్.
What do you mean by rotor acceleration?
d² delta by dt square.
That ratio itself is that value, right?
yes సార్.
Accelerating power per unit acceleration
ఓకే సార్.
is accelerating power by acceleration you have to take, right?
ఓకే యాక్సిలరేషన్ పవర్ బై యాక్సిలరేషన్.
Acceleration.
ఓకే.
That is nothing but M.
yes సార్. బై ఫార్ములా.
Hmm.
ఓకే. ఇన్ 135 F. no this 1 minute. no this one not sir. సార్ ఇప్పుడు 139 F సార్. టై లైన్ చెప్పారు కదండి సార్ ఇప్పుడు డిస్కనెక్ట్ అయిపోతే అది లోడ్ గా యాక్ట్ చేస్తుంది అని.
Not
మామూలుగా
load actually.
Ah.
After disconnecting this tie line, if you replace this area to its equivalent circuit,
ఓకే.
you will have a voltage source in series with the reactance.
ఎస్ సార్.
Then whenever you are connecting this tie line, so as you have a voltage source in series with the reactance, but is
Okay.
drawing some power,
ఓకే సార్.
it's an equivalent of synchronous motor, right?
ఎస్ సార్.
That's it. That's what I said earlier.
మామూలు టై లైన్ కి నార్మల్ డిస్ట్రిబ్యూషన్ లైన్ కి డిఫరెన్స్ ఏముంటుంది సార్? సార్
Yeah.
సార్ టై లైన్ కి
One
నార్మల్.
minute.
ఓకే.
For example, this is one area,
ఓకే సార్.
and this is the second area.
ఓకే సార్. ఓకే
So
సార్.
in this area, you have some generator, okay, line. This is one more line connected to transformer. We have one more line like this. We have some system,
ఓకే సార్.
and we have here also some generator, transformer, line, right? Connected
Okay.
to one more transformer, something like this here.
ఓకే సార్.
And this is one bus bar in this system, and this is the other bus bar in this system.
ఓకే సార్.
These two are connected by this transmission line wire. Transmission line.
ట్రాన్స్మిషన్. ఓకే సార్.
Okay. See, for example, inside this network, all the buses almost interconnected.
ఓకే సార్.
For example, if you disconnect this line, one line, you disconnect.
ఓకే.
Can I say it is going to cause a complete disconnection between the two buses?
కంప్లీట్. నో సార్. నో.
May not. Why in the sense this bus might be indirectly connected to this one by some other way, right?
ఓకే.
We have not shown completely, strictly speaking.
ఎస్. ఎస్ సార్.
This may be some other line connected to this generator, and it may be connected something like this.
ఎస్ సార్.
Okay, even though you disconnect this line, but still it is connected to this bus by some other way, right?
ఎస్ సార్.
Okay, even though one channel was closed, one channel was open, means you don't have way in one side,
ఓకే.
but you have a way on the other side and you can come back.
ఎస్ సార్.
But if you disconnect this transmission line wire, is there any connection between these two buses at all?
నో సార్. నో సార్.
This line specially called as tie line.
ఓకే సార్.
Okay.
Got it, sir.
If you disconnect that line, there is no connection between the two buses further.
Okay, sir. Okay, sir.
Yeah.
Sir, 139 F, sir.
139.
Yes, sir. విత్
You
ఇక్కడ
lost
ఫాల్ట్
it.
ఇప్పుడు ఫాల్ట్ జరిగితే సార్ ఇక్కడ
Where
మిడిల్ ఆఫ్ ది ట్రాన్స్మిట్ టై లైన్.
middle of the tie line. Yeah. For example, so this is one area
ఓకే సార్.
consisting number of generators, and this is the other area, area 2, consisting number of generators again.
ఓకే సార్.
Okay. So in this area, the power generation is PG1. Power generation is 3000 megawatt.
ఓకే సార్.
Load, I am saying PD1 demand.
ఓకే సార్.
It is, let us say, 2600 megawatt.
ఓకే సార్.
And in this area, the power generation PG2 is 2600 megawatt. Generation 2200 megawatt. But you have a demand of 2600 megawatt here.
ఓకే సార్.
There's a mismatch.
ఎస్ సార్.
In one area, generation is more, demand is less.
లెస్.
Other area, generation is less, demand is more. Okay.
ఎస్ సార్.
So to meet this power demands and all, I am joining these two areas by using one line called as tie line.
ఓకే సార్.
Then how much amount of power this tie line has to carry?
400.
400 megawatts in the given direction.
ఎస్ సార్.
So in the healthy operation, without any short circuit fault, anything, we have a power generation of 3000, local load 2600, remaining 400 megawatt will go into the tie line, enters into area 2.
ఎస్ సార్.
In the area 2, generation 2200, local load is 2600. The excess 400 will be taken from the tie line.
ఓకే సార్.
Now, if you have a short circuit fault on the tie line, okay.
ఓకే సార్.
Yeah, a short circuit fault on the tie line.
టై లైన్
Then what will happen to this tie line power flow?
బికమ్స్ 0.
0. So there is no power exchange between the two systems.
ఎస్ సార్.
If that's the case, in the first area you observe, how much is generation?
3000.
How much is the load?
2600.
Means generation is more compared to demand.
ఎస్ సార్.
Input energy to the system is more compared to output energy.
ఎస్ సార్.
Where the excess energy has gone.
టై లైన్.
Tie line output is 0, right?
ఎస్ సార్.
You should think about it. We have a
Loss.
system. Listen, we have a system. You are giving some input energy. We are getting some output energy.
ఎస్ సార్.
Output energy is less compared to input energy.
ఎస్
Means
సార్.
input energy is more.
ఎస్ సార్.
Where the difference has gone. Store it into system, right?
ఎస్ సార్.
Store it into system means what?
కైనెటిక్.
Water, kinetic energy.
ఎస్ సార్.
Then whatever the generators we have in this area will accelerate.
ఎస్ మోర్ యాక్సిలరేషన్.
Acceleration. Okay.
ఎస్ సార్.
And in this area, generation 2200, demand is 2600. Your input energy was less compared to output energy.
ఎస్ సార్.
Then who is supplying that excess output energy demand?
రోటర్ స్టోర్ చేసుకునే
Rotors.
ఎనర్జీ.
Then what will happen to these machines?
డిక్రీస్ ద స్పీడ్.
Acceleration.
ఎస్ సార్.
Once one group of machines are in acceleration, other group of machines are in deceleration.
బోత్ ఆర్ నాట్ స్వింగింగ్.
These two groups are not swinging together.
ఎస్ సార్. క్లారిటీ. గాట్ క్లారిటీ.
Yeah.
సార్
Any other doubt? Tell me.
సార్ యాక్సిలరేటింగ్ పవర్ అంటే మామూలుగా మనం యాక్సిలరేటివ్
This
బాడీ
is
నుంచి
the accelerating power means it is a power which is causing for acceleration of rotor.
ఓకే సార్.
Input power minus output power to the rotor.
ఓకే సార్. ఇన్పుట్
Input
పవర్
mechanical, output electrical in case of generator.
ఎస్ సార్.
In case of motor, input electrical, output mechanical.
ఎస్ సార్. ఓకే గాట్ ఇట్ సార్. ఇన్ లాస్ట్ 155 ఎఫ్ సార్.
Yeah.
సార్ అక్కడ లాస్ట్ యూనిట్స్ రాశారు కదండి సార్ దీనికి. ఇక్కడ పర్ యూనిట్ రాసినప్పుడు మెగావాట్ ఎంవిఏ అది
That's your
అర్థం.
wish. Megawatt by MVA is per unit.
ఎస్ సార్.
You can write it as per unit megawatt also.
పర్ యూనిట్ మెగావాట్ అని కూడా రాయచ్చు.
You can write it. In some
లేదంటే per unit-
materials and all the people will write, you should not write it as per unit megawatt. You see,
yes.
many textbooks are giving per unit megawatt second. Means it is allowed, right?
ఓకే సార్. పర్
Megawatt
యూనిట్
only. Megawatt by MVA is a per unit, sure.
ఎస్
But
సార్.
I am saying it's per unit megawatt. By looking at that, you have to understand that, okay, you have written per unit megawatt means it's megawatt by MVA.
ఓకే సార్.
That's it.
గాట్ ఇట్ సార్. ఎస్టర్డే ఒక డౌట్ ఉంది సార్.
Tell me.
1 minute సార్. ఇప్పుడు ట్రాన్స్ఫార్మర్ ఉన్నప్పుడు పర్ యూనిట్ ఫామ్ లో కాకుండా నార్మల్ ఫామ్ లో మిగతావన్నీ తీసుకొని దాని ఇంపిడెన్స్ ని మళ్ళీ అబ్సల్యూట్ కన్వర్ట్ చేసి చేయకూడదా సార్ మనము?
You can do it. If you take all the impedance onto one side of transformer,
ఓకే సార్.
you can do it.
అంటే ఇప్పుడు ట్రాన్స్ఫార్మర్ కి నిన్న మనం ఒక ప్రాబ్లం అక్కడ ఇంపిడెన్స్ ఇచ్చారు సార్ 0.2 పర్ యూనిట్. దాని బేస్ వాల్యూస్ మనం ఏమైతే అనుకున్నామో ఆ బేస్
Ratings.
వాల్యూస్. ఓకే
Ratings are base values, right?
ఓకే అవి కన్సిడర్ చేసి చేయండి.
That is the effective impedance of transformer referred to any side, primary or secondary.
సెకండరీ. ఓకే సార్. ఇంకొకటి సార్, నిన్న మనము P maximum is equals to V²/4R కనుక్కున్నాం కదండి సార్.
Yes.
అది మాక్సిమైజ్ పవర్ కనుక్కున్నాం సార్ మనము. అది మరి ఎఫిషియన్సీ తక్కువ ఉన్నప్పుడు ఎందుకు యూజ్ అవుతుంది సార్ అది మరి ఇంకా మనకు?
That's why we are not using it.
ఓకే.
What is the ultimate maximum value we done?
ఓకే సార్.
But still we are not using it means we are having a problem of efficiency.
ఓకే. ఓకే సార్. గాట్ ఇట్ సార్.
Okay.
థ్యాంక్ యూ సార్.
Sir.
Sir, good evening, sir.
Tell me, sir.
Sir, in page number 146.
Okay.
Not, sir. I think next page. Next page 148. Set example. Sir, here we cannot write formula M equivalent equal to M1 M2 by M1 plus M2.
Like that also you can write.
Then
You can write here M1 M2 by M1 plus M2 also you can write.
then we will not get M1, sir.
That's why I am following this one. Both are same, right?
Yes, sir.
M1 M2 by M1 plus M2. If you take infinite by infinite, you are going here.
Yes, sir.
You are unable to get it from that. Same equation I have rewritten like this.
Okay, sir. Okay. Sir, another doubt. In last problem, generator rating was given 50 MVA. No, sir.
Yes, yes.
There we got kinetic energy, some value, no, sir. So if we take another rating, means somewhere 100 MVA or something, but we'll get the same kinetic energy, no, sir.
Again, J value of that rotor may be different. You know.
Okay.
Inertia constant of the rotor may be different. For example, the same generator with the same J designed for 100 MVA.
Okay, sir.
Then your inertia constant will become 0.987.
Okay, sir, I got it, sir. Thanks. That's it.
Okay. Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, is swinging together is a sufficient condition for parallel operation of alternators, sir?
Can't say exactly. We are talking only in the manner of real power here. We are not
Yes.
talking in the manner of voltages.
If voltages are equal, then it is sufficient, sir.
Yes. Voltage should be equal, phase sequence should be same, frequencies must be matched.
Sir, and that means delta 1 is that both deltas are equal, no, sir. That means both have phase sequence should be same, no, sir.
Maybe yes, correct. What you said is correct. But
Yes.
only swinging together may not be sufficient.
Yes, sir. Only swinging together, not, sir. One of the condition for parallel objects.
Yes, you can see it.
Okay, sir. Sir, I have sent you 2 questions, sir. That
Which questions?
sir, the gate question, sir. That fault analysis.
Okay. I will discuss it tomorrow. That fault. Have you seen solution for it?
Sir, I have seen solution for 10th one, sir. Sir, but that diagram representation I want, sir. Where that means I'm not understanding. Even means అంటే ఇప్పుడు ఫస్ట్ బస్ దగ్గర ఏ ఉంది సార్, సెకండ్ బస్ దగ్గర బి నోట్ తీసుకున్నాను సార్. సార్ ఇప్పుడు ఏ దగ్గర ఫాల్ట్ రావడం వల్ల అంటే బి దగ్గర
problem that I have discussed I think last year also in JetBus I have discussed it.
Yes sir. Yes sir. In load flow I have discussed, sir.
JetBus not in load flow.
Yes sir.
Both readings.
Okay sir.
I think that phasor diagram also I discussed last year, that IF1, VF1, IF2, VF2.
Yes sir, you have discussed.
Some doubt session only, not in regular class. In doubt session only I might have discussed. Okay, go through it. If you have still any doubt, we'll discuss tomorrow.
Okay sir.
Okay.
Okay sir. Thank you sir.
Yeah. OP. OP Raju. Do you have any doubt? OP Raju. Sai Chiran. Sai Chiran.
Hello, sir.
Tell me, Sai Chiran.
Sir, for stability, you told 2 types. In case of that power equations and this another method. For both of them, did we got the same thing, sir?
Same thing you will get.
Then we told that it would be more exact than this power equations, sir.
Actually, if you have a small disturbance, either you do the stability analysis by using swing equation or power equations, it will give same result.
Okay, sir.
If you have a large disturbance, doing stability analysis with power equations is not a problem.
Okay, sir.
You should go with the swing equation only.
Here in stability analysis, steady state stability, the methods we did not, sir. This method will not be applicable for this. This method will not be applicable for this, sir. This exact method.
Which exact method?
We discussed today, sir.
There we discussed
Combining
about swing equation, solution of swing equation for small disturbances.
Yes, sir. For this
That is
solution
nothing but steady state stability.
Yes, sir. We also discussed about a steady state stability for by using swing equation, sir.
Have you understood the first statement? What is it? Steady state stability analysis can be done either by using swing equation as well as by using power equations.
Yes, sir. I understood, but the methods to improve system stability would be according to this power equations, no, sir.
What you said there to improve the steady state stability of system?
Maintain loading that all related to
basic
power.
one you did. Basic one. What is it?
Maintain rate of power with respect to delta.
Yes, very high.
Yes, sir.
What is the equation for that?
Pmax into cos delta naught.
That's what we have done. That's what we said here also, right? In swing equation.
Yes, sir. That is only my doubt, sir.
What do you have doubt in that again? Same thing
No,
I
sir,
said again.
is that same only?
Same only. We have written same equation. Pmax cos delta naught, right?
Okay, the whole system is same, but analyzing is two different ways.
Analysis in two different ways you can achieve it.
Okay, okay. Okay, sir.
Final result is same. On what state, on what quantities the system stability will be depending means again synchronizing power coefficient, P maximum cos delta naught.
Okay, okay, sir.
If that is very high, your poles will lie definitely on the left side of S plane, system will be stable.
Okay, sir. Sir,
If that is very high, you are saying in the positive slope region, system will be stable.
Okay, sir. Sir, here in this root locus, sir, we took k is equals to 0 now, sir.
Hmm.
Okay. But k would not be 0 for practical case, no, sir?
Why? Practical case, it may or may not be.
I'm telling that the initial power would not be 0 or not, sir.
Initial power.
Initial that operating Pmax into cos delta. That one.
It won't be
That would
0.
not-
Okay.
So k would not also be 0. No?
If K is becoming 0, then you are going to get roots at that place, right?
Okay, we are analyzing that if that k would be 0, then what would be the system marginal stability? But we are not saying that it is k is equal to 0.
I think you are thinking that, sorry, in root locus, we studied from K equals 0 to K equals to infinite.
Yes, sir.
Is it you are thinking?
Yes, sir. Yes, sir.
What is that K and this K? K, okay.
Constant. We took that
K,
delta.
it's okay. That is gain there. This is different term, right?
This both are equal only, na, sir. K here we took a constant, but Pmax like we are assuming that Pmax into that cos delta would be constant. So
Will
the
your
K
system,
on,
sorry, okay, you have drawn a root locus for a system.
yes, sir.
Will that system knows that I have to start K value with 0 only? Is it no?
No, sir. No, sir.
For certain value of K, your roots will fall at some point on the root locus.
Okay, okay, sir.
If you understanding?
Yes, sir. Yes, sir.
System will not place a root locus, right?
Okay, sir.
We are tracing it for the analysis.
Okay, okay.
System will fall at one point in the root locus. It won't trace the complete root locus.
Okay, sir.
Understood?
Yes, sir. Yes, sir.
Yeah.
Sir, here initial conditions here we took power output, na, sir. Power output P.
Yeah.
Delta naught. This delta naught would be this would be anything, na, sir. Delta naught.
Anything. Initial operating point. Anything. That's your wish.
Okay. But initial operating point should be in stability or delta naught, sir.
Oh,
In
see,
stable
whichever
region.
you take your initial operating point, whichever you take delta naught value, that's your wish. What you consider?
Okay, sir.
With respect to the delta naught value, calculate K.
Okay, okay, sir.
After calculating K, locate the roots in the plane.
Okay, sir.
That roots will fall on the root locus, correct?
Okay, sir.
Okay, and after checking the roots, whether these are on the left half of S plane or right half of S plane, that decides the system stability.
Okay, sir.
Okay.
Yes, sir. Yes, sir.
Any more doubts you have, Sacharan?
Okay, sir. That's it.
That's it. Okay. Anybody having a doubt? Please raise your hands. Ajay. Ajay.
Hello, sir.
Tell me, Ajay.
Sir, into equation is 1 by m1 is equal to 1 by m1 plus 1 by m2 dash dash. అది అర్థం కాలేదు సార్. Sorry.
You have not understood here. Somebody said resistances in parallel. It's like that also.
They're not swinging anything.
Yes. M equivalent 1 equals to M1 M2 by M1 plus M2.
Yes, sir.
We have only two machines. You can write M equivalent 1 is M1 M2 by M1 plus M2, right?
Yes, sir.
This you can rewrite as 1 by M1 plus M2 by M1 M2.
Yes, sir.
This is nothing but 1 by M2 plus 1 by M1.
Yes, sir.
And this is 1 by M equivalent 1.
Yes, sir.
What you can write from this?
1
1 by
M
M equivalent 1 equals to 1 by M1 plus 1 by M2, right?
Yes, sir.
Like that you can write.
సార్ అంటే ఒక దగ్గర ఉండే ఇట్లాంటి ఈ కండిషన్ లో ఎన్ జనరేటర్స్ కనెక్ట్ అయినప్పుడు నాట్ స్వింగింగ్ టుగెదర్ అని ఒక చెప్పింది కదా.
Generally, if anybody asks you machines are not swinging together, they will ask you only with respect to two generators. Okay, if you have many number of generators, converting that into a single generator by using this equation may not be preferable.
Okay.
But swinging together you can apply.
Okay.
Swinging together will not have any much restrictions. You can apply it.
Okay.
But not swinging together, you can't apply anywhere you want, generally.
Okay.
Okay?
ఓకే సార్, అంటే స్విమ్మింగ్ లేనప్పుడు ఈ ఈక్వేషన్ యూజ్ చేయడానికి రాదు కదా సార్. ఒక జనరల్ డౌట్ సార్, ఇప్పుడు మామూలుగా ట్రాన్స్ఫార్మర్ ఓన్లీ కేవీఏ రియాక్టివ్ పవరే కదా సార్ సప్లై చేసేది?
Reactive power.
కేవీఏనే కదా సార్, కేవీఆర్ సప్లై.
KVA, not KVR. KVA, apparent power.
అపరెంట్ పవర్ కదా సార్. అంటే ఆల్ లోడ్స్
rating of apparatus is in KVA, not power, not real power reactive power. Simply we are saying apparent power rating is KVA, and that the only apparent power supply chestunnaru, meaning adi will supply both real and reactive powers. How can you understand like that, Ajay? An apparatus is rated for certain rating. KVA or MVA means that is a rating of the apparatus. That's it. That does not mean that it is not going to supply real power, reactive power. It will supply only apparent power.
Okay.
Understood? Yeah. That's it.
సార్, ఇంకొకటి మామూలుగా ఇప్పుడు ఈ స్టెబిలిటీ అనాలిసిస్ అనేది ఓన్లీ మనం ఈ సింక్రోన్ మోటార్, సింక్రోన్ జనరేటర్ చదువుతాం కదా సార్. అంటే ఒకవేళ ఇప్పుడు మన సోలార్ కానీ విండ్ కానీ కనెక్ట్ చేసినప్పుడు స్టెబిలిటీ అనేది ఉండదు కదా సార్.
There also you have stability analysis. It may be a voltage stability analysis. Frequency stability will be also there, but that is on the already existing system. We may not study this angular stability analysis for solar system or wind system.
Sir.
Voltage stability, right?
Yes.
Those things we will do in that.
Okay. సార్, ఇంకొక డౌట్, మామూలుగా మనం ఏసీ ట్రాన్స్మిషన్ లో వోల్టేజ్ అనేది ఎక్కువ కాన్స్టెంట్ ఉండడానికి యూజ్ చేస్తాం. ఒక డీసీ సిస్టమ్ అయితే ఎట్లా సార్, అంటే కరెంట్ యూజ్ చేస్తాం సార్, అక్కడ ఓన్లీ వోల్టేజ్ అని.
Why you can you tell me the first statement what you said?
ఏసీ ట్రాన్స్మిషన్ లో మనం మాక్సిమం వోల్టేజ్ అనేది కాన్స్టెంట్ ఉండడానికి ట్రై చేస్తాం కదా సార్.
Okay.
కాన్స్టెంట్ ఉండడానికి ఈ డీసీ సిస్టమ్ లో
This system also will attempt to go for voltage.
సార్, ఈ మాక్సిమం అంటే ఇందాక చెప్పింది కదా సార్, Pmax అనే స్టెబిలిటీలో ఓన్లీ సర్క్యూట్ కెపాసిటీ అని. అంటే టూ సైడ్స్ ఇప్పుడు సింక్రోనస్ మోటార్, సింక్రోనస్ జనరేటర్ కనెక్ట్ చేసినప్పుడు అక్కడ బోత్ అనేది పవర్ అనేది జనరేట్ చేస్తాయని, అందువల్ల
అది అందువల్ల అది Pmax అని ఉంటుందా సార్, లేకుంటే ఒకవేళ
Can you repeat it again, Ajay? What you asked?
అంటే ఇప్పుడు
We have a
Generator.
generator and motor, you said.
సార్ అంటే బోత్ రెండు పవర్ ని జనరేట్ చేస్తాయి కదా సార్, అంటే ఒకటి పవర్ తీసుకుంటే ఒకటి పవర్
Okay.
జనరేట్ అయ్యాయి.
Okay,
కానీ
okay.
సార్ ఒక కండిషన్ లా సమ్ టైమ్స్ అంటే ఇప్పుడు ఎగ్జైటేషన్ మోటార్ కి ఇంక్రీజ్ చేసినప్పుడు ఇది మోటార్ గా ఈ ట్రాన్స్మిషన్ లైన్ కి వోల్టేజ్ పంపిస్తుంది కదా సార్, అంటే పవర్ పంపిస్తుంది కదా సార్.
Will motor will supply power to line?
ఎస్ సార్,
It's power.
మేబీ రియాక్టివ్ పవర్, రియాక్టివ్ పవర్ ఆర్ యాక్టివ్ పవర్.
How motor will supply active power, Ajay?
రియాక్టివ్ పవర్ సార్, యాక్టివ్ పవర్ అంటే కండెన్సర్ యూజ్ చేస్తాం కదా సార్.
Okay, okay.
ఇప్పుడు బోత్ అనేది సప్లై చేసినప్పుడు Pmax అనేది డిక్రీజ్ అవుతుంది సార్.
Pmax depends upon your network elements, right? Network elements and these voltages, that's it. It won't depending on your operating condition, right?
Yes.
Pmax formula is what? Eg Em by X equivalent.
Yes sir.
Will it depends upon how much current flowing in the line?
No sir.
Will it depends upon what you said, reactive power and all here?
No sir.
It depends upon only voltage sources and network impedance, irrespective of how much current or how much reactive power you are sending.
Okay, sir.
But what you said earlier is, if you are changing excitation of this motor, once after changing excitation of this motor, EM value will change. Because of that, Pmax will change, not because of network change. Because of voltage variation, there is a change.
Okay.
Okay, Ajay?
Thank you sir.
Ajay, tell me if you have any more doubt in this.
No sir, అంటే ఇవే ఉన్నాయి సార్ డౌట్స్.
Okay, fine.
Thank you sir.
Yeah. Gopi Raju. Gopi Raju.
Hi sir. Yes sir.
Tell me Gopi Raju.
Are you audible my voice?
Yeah.
Yes sir. I was some work on question. What are the expression derived swing equation? A single generator connected to the bus bar system. Is it applicable for two or more generators connected to the same bus bar system? Is it applicable for same equation?
Oh, you are saying that two generators are connected to same bus
Two
bar.
generators are greater than two. Generators are connected to the bus bar. Is it single equation valid for this or not?
You derive swing equation if you have two or more number of generators.
Is it same equivalent to the whatever done by only single generator? Is it same procedure, sir?
You calculated swing equation. Okay.
That's yes, sir. Same procedure followed by the...
Listen.
Okay.
Calculated swing equation for one generator.
Okay.
After that, we studied combining machines theory.
Yes, sir.
There we have seen how to convert number of units into a single unit.
Yes, sir. That's my question. But in some more textbooks, swing equation derived by single generators is not valid for two greater than two. Some textbooks are said. That's why I asked this question.
If you have the textbook, please send to me. I will also read it.
Okay, sir.
You send in Telegram.
Okay, sir.
I will also go through it and I will tell you in what condition they have taken that statement.
Okay. I understood.
There might be some conditions. Might be some conditions. Without that, they don't tell it as
Oh no. Some
they
more
might be
clarity.
saying in the way of non-swinging case.
Okay.
Machines are connected but not swinging together. Then more than two machines you may not use. It means you may not use the equation what we have derived.
Okay.
Swinging together, there is no restriction. If you connect any number of units to the same bus bar running in parallel like machines, will swing together.
Okay. Converted into the single generator.
Single
then we-
generator by using that M equivalent equals to M1 plus M2 and so on. N.
Okay. That is not applicable for not swinging, sir.
Not swinging together, generally we don't apply for N machines.
Okay.
Hardly we go for 2 machines there.
Okay. Sir, by studying
You
the
have,
study.
you have a formula for N machines also.
Hmm.
You can calculate by using that N machines formula.
Okay.
You will get some number. You can do the analysis.
Hmm.
But the analysis result, we can't do anything with that because practical thing might be completely far away from the analysis what you have done.
Okay.
So that's why that formula is not applicable to the conversion. There are some other techniques like equivalent techniques and all. By using that, they will calculate M equivalent.
Okay. Sir, second question. As per the generating present practical generating station, if there is any happens in the network, as per the in point of view, whether it is under steady state stability or transient stability, how do they know? That's my question, sir. If it happens, anything happens in the transmission network. That is under the steady state stability category or transient stability category. How do you know? If it is, how can you justify? That's my question.
For that purpose, we will be keeping sensors and all, right?
Okay, practical, sir.
Practically, definitely if you have a problem of transient stability, that may be because of line removal, or it may be because of a fault.
Okay.
Or it may be because of failure of steam supply to the generator.
Okay.
Or the sudden addition of load.
Okay.
All of a sudden, you experience a frequency variation greatly.
Okay.
All of a sudden, if you are observing under frequency or over frequency at various places by means of relays, particularly at generating stations,
Okay.
it is an indication that there is some major thing happened in the system.
Okay.
If the frequency is increasing, decreasing continuously, but still it is within the limit,
Yes.
then we feel that there is nothing happened in the system. Some small disturbance are continuing in the system.
Okay. That is under the category of steady state stability.
Steady state. If you have a great variation in the frequency,
Okay.
if you sense it in that manner, then something happened in the system.
Okay.
We have to take some necessary action.
Okay. Okay, sir.
Yeah.
Yes.
Any other doubt you have, Gopi?
Yes, sir. One more question. In the yesterday class, we derived maximum power transfer through transmission network. If you can place a loading equals to P maximum, we get very less efficiency. Then my question is, at what optimum level we can place a loading such that efficiency of the transmission network is more?
What extent means
Up to what
minimizing loss you are
approximate?
saying?
Yes, sir.
Minimizing loss you are saying.
And if you can place loading equals to P maximum, efficiency of the transmission network is very low, you said yesterday.
Yes.
My point is, up to what optimum level loading you can place on the transmission network such that I can get more efficiency? Which parameters can decide?
More efficiency means how much efficiency you want?
How much efficiency is my point of view? Transmission network efficiency near to 85-90.
Then with respect to that 85% efficiency, you have to calculate power loss.
Okay.
Getting?
Yes, sir, getting.
According to that, you have to decide how much load you have to keep.
P maximum can be calculated only deciding how much load we can place in future. That is the only point of view.
That's the limit. What's the name of P maximum?
That is the SSL, steady state stability limit. Limit. Okay, sir.
Yeah.
Yes, sir.
That's it.
That's it, sir.
Any other doubts? Please raise your hands. Murali Krishna.
Sir, good evening, sir.
Tell me, Murali Krishna.
Sir, అది ఒకటి ప్రాబ్లం ఉంది చూడండి సార్, స్టేషన్ ఏ, స్టేషన్ బి, స్టేషన్ సి.
Yes.
సార్ అక్కడ ఒకటి అబ్రివేషన్ టైప్ లో ఒకటి ఉంది సార్, అది ఎస్ఎం, అది ఫుల్ ఫామ్ ఏమొస్తుంది సార్ అది?
ఎక్కడ
అదే SMIB
సింగిల్ మెషిన్ కనెక్టెడ్ టు ఇన్ఫినిటీ బస్ బార్.
సింగిల్ మిషన్
Connected to
కనెక్టెడ్ టు
infinite bus bar.
ఇన్ఫినిట్ బస్. ఓకే సార్, ఇక్కడ M అని ఇండికేట్ చేసాం
Means
కదా సార్.
if you are converting these two into a single, so I can
Sir.
draw in this manner, right? Whole system.
ఆహా, ఓకే. ఐ మీన్ సింగిల్ లైన్ డయాగ్రామ్ అన్నట్టుగా సార్.
Single line diagram,
ఓకే
a single
To a infinite bus
synchronous machine
bar.
connected to infinite bus.
ఓకే, ఇక్కడ M అని ఇండికేట్ చేసింది అది సింక్రోనస్
Angular momentum.
యాంగులర్ మూమెంట్
Angular
సార్ అవి.
momentum. Yeah. ఇక్కడ చెప్పాను problem.
ఓకే సార్, ఓకే సార్,
Each unit angular momentum is given in the figure.
ఓకే సార్, ఓకే సార్. అదే సార్, ఈ వాళ్ళంతా మొత్తం డెరివేషన్స్ ఎక్కువ ఉన్నాయి ఇది. అయితే ఇప్పుడు ఈ అంటే వాటిలో ఏది అంటే మేము గుర్తుపెట్టుకోవాలి ఏది అనేది అర్థం కావట్లేదు. అంటే యాక్చువల్గా ఈ ప్రాబ్లం బేస్ కోసమేనా సార్ అదంతా డెరివేషన్?
Yes.
అంతేనా
You
సార్?
practice problem, then you will come to know what
Yes,
you have
sir.
to remember.
ఓకే సార్, ఓకే సార్. సార్ ఇంకొకటి లాస్ట్ ఒకటి ఎగ్జాంపుల్ చెప్పినారండి సార్, అది పవర్ జనరేషన్ 3000 మెగావాట్
Yes,
డిమాండ్
yes.
అని. ఇప్పుడు మామూలుగా అది లాస్ట్ గా పవర్ స్వింగ్ అనేది ఉంటుందా లేదనేది అది లాస్ట్ కి అర్థం కాలేదు సార్. అది ఉంటుంది కదా సార్ మామూలుగా ఐలైన్ అనేది ఏం బ్రేక్ లేకున్నట్లుంటే పవర్ స్వింగ్ లో ఉందని చెప్పొచ్చు కదా సార్.
Power swing is different word, Murali Krishna.
సార్
Power swing is a different word.
సార్
Power swing means a large variation in the power. That's it.
సారీ సార్, ఐ మీన్ స్విమ్మింగ్ అదేదో అన్నా సార్.
Swinging
Swing-
together or
swing.
not swinging together.
ఓకే సార్, అదే అది బ్రేక్ లేకుంటే స్వింగింగ్ అని చెప్పొచ్చు కదా సార్.
Even you don't have a break on the tie line,
Okay.
fault on the tie line, still you should
Okay,
say
sir.
both areas are not swinging only
ఓకే సార్, ఓకే సార్. ఇంకొకటి సార్, ఇప్పుడు
because angles are not equal.
ఓకే సార్, ఇప్పుడు ఇక్కడ ఏరియా 1 ఏరియా 2 అదే బ్రేక్ అయినప్పుడు ఇది యాక్సిలరేటింగ్ డియాక్సిలరేటింగ్ అని చెప్పినారు కదా సార్. ఓకే, ఇన్ కేస్ ఫాల్ట్ రెక్టిఫై అయినప్పుడు అంటే అప్పుడు ఏమవుతుంది సార్? అప్పుడు వాటి అంటే ఏరియా 1 యాక్సిలరేషన్, ఇక్కడ ఏరియా 2 యాక్సిలరేషన్ అనేది దాని నుంచి ఏమైనా ఎఫెక్ట్ ఉంటుందా రెక్టిఫై
After
అయినాక?
that fault has been cleared, immediately
ఓకే సార్,
we may have some small value of tie line power, and of course immediately we have a new angular difference between the two areas, right?
ఓకే సార్,
For example, delta 1 minus delta 2 is an angular difference.
ఓకే
Initially, before occurrence of fault, we have some 20 degree.
ఓకే సార్,
20 degree is constant, continued.
ఎస్ సార్,
Fault occurred.
ఓకే
After the fault occurred, the delta 1 minus delta 2 will go high, maybe 20, 21, 22, 23, like that it will increase.
ఓకే సార్,
At the instant when you are clearing the fault, there is some angle, right?
ఎస్ సార్,
Is within the time from the instant of short circuit to the
Okay,
point
sir.
of clearance.
ఎస్ సార్,
In that gap, delta
Yes.
1 minus delta 2 might have increased to some value.
ఓకే సార్,
Maybe in that time duration, the angle was increased from 20 to let's say 30 degree.
ఎస్ సార్,
Okay. At the instant of fault clearing, how much is the angle difference? 30 degree.
30 డిగ్రీ, ఎస్ సార్,
With respect to 30 degree, that power will be transferred.
ఎస్ సార్,
Understanding? But
ఎస్ సార్,
with respect to 30 degree, if it is transferring, but still
Yes.
we have a power imbalance.
ఎస్ సార్,
Why in the sense? If the angle is 20 degree, there is a power balance exactly.
ఎస్ సార్,
But if the angle is 30 degree, you have a power imbalance, right?
ఎస్ సార్,
Because of that, due to mismatch, after
Yes,
some
sir.
time, this area may decelerate. Area 1 may decelerate.
ఎస్ సార్,
Area 2 may accelerate again.
ఓహో, ఎస్ సార్,
And the deceleration will be continue. At some point of time, this angle will come back to 20 degree
ఎస్ సార్,
and powers will settle down. And
Okay, sir.
acceleration, deceleration will die down.
ఓకే సార్, ఓకే,
There we say we reach to steady state after the transient has gone.
ఓకే సార్,
Okay?
ఓకే సార్, ఓకే. సార్ ఇంకోటి సార్, మీరు మాకు అదే ఈ పిఎస్సీనా సార్ ఇంకా వేరే ఏమైనా డీల్ చేస్తారా సార్?
Don't ask me like this.
ఓకే సార్, ఓకే సార్.
Okay.
సార్ ఇంకొకటి యాక్చువల్ అంటే అదే సార్, ఇప్పుడు మీరు ఇక్కడ ఇప్పుడు మీరు చెప్పే ప్లేస్ లో కొన్ని ఎప్పుడన్నా ఒకసారి వర్డ్స్ కొన్ని మిస్ అవుతున్నాయి సార్. అంటే వాయిస్ మధ్యలో
Okay.
బ్రేక్ అవుతుంది. ఇంకొక రూమ్ అయితే ఓకే. అక్కడ ఏమి అనిపించట్లేదు నాకు అనిపించింది మరి.
I have some problem. That's why I will be thinking always in the view of student comfort only.
Yes, sir. Yes, sir.
So I do know that that room is more comfortable to the students to listen the class.
Yes, sir. Yes, sir. అవును సార్.
I have my own problem why I am teaching in this room. Okay? Yeah. Which I can't reveal.
సరే సార్. ఓకే సార్. సార్ ఇంకొకటి సార్, మన ఇండియన్ ఫ్రీక్వెన్సీ ఎందుకు సార్ 50 హెర్ట్జ్ పెట్టాల్సి వచ్చింది సార్? వేరే కంట్రీ లాగా 60 పెట్టచ్చు కదా?
No, that UK people has designed the power system network in India.
Sir.
They have their frequency as 50 hertz. They established their own system at 50 hertz.
Yes, sir.
With the same frequency, they have gone here also.
Yes, sir.
Why they have gone for 50 hertz? Why the American people gone for 60 hertz? That is due to their business and trade issue.
Yes, sir.
Because after UK has established their system at 50 hertz,
yes, sir.
American people started their construction of our system.
Yes, sir.
And for example, American people have chosen that frequency as 50 hertz only.
Yes, sir.
Then from UK, the electrical goods will flourish like anything into US.
Yes, sir.
That may be a threat for the US companies, manufacturing companies.
Yes, sir.
Because of that reason, US people adopted 60 hertz. So
Yes,
that we
sir.
have a frequency mismatch, so that the electrical goods, fans, lights, other equipment,
Sir.
which UK people designed for 50 hertz frequency,
Yes, sir.
may not be suitable for 60 hertz.
Yes, sir.
అర్థమైందా?
Sir.
ఆల్రెడీ మీ డివైస్ అన్ని 50 హెర్ట్జ్ ఫ్రీక్వెన్సీకి డిజైన్ చేసుకున్నారు కదా యూకే లో.
సార్.
అలా ఉన్నప్పుడు యుఎస్ వాళ్ళు 60 హెర్ట్జ్ ఫ్రీక్వెన్సీ తీసుకుంటే
సార్,
ఆ ఎలక్ట్రికల్ గూడ్స్ అన్ని ఇటువైపు రాలేవు కదా, ఇటువైపు ట్రాన్స్ఫర్ కాలేవు కదా.
అవును సార్, అవును.
అందువల్ల యుఎస్ కంపెనీస్ ఖచ్చితంగా ఎఫెక్ట్ అవ్వవు.
సార్.
యుఎస్ కంపెనీలు వాళ్ళు 60 హెర్ట్జ్ ఫ్రీక్వెన్సీ దగ్గర ఎలక్ట్రికల్ గూడ్స్ వాళ్ళే డెవలప్ చేసుకుంటారు.
అవునండి సార్.
ఆ ఛాన్స్ ఇచ్చినట్టు అవుతుంది.
Yes, sir.
That's why they have adopted different frequencies.
Yes, sir.
అంతే.
Okay, sir. In last doubt, sir.
Technically speaking, 50 hertz is more comfortable as compared to 60 hertz.
60. Yes, sir. Sir, last doubt, sir. నేను అదే ఏంటంటే మామూలుగా జనరేట్ చేసే వోల్టేజ్ 11 kV అని ఉన్నాను, అది కరెక్టేనా సార్? మామూలు జనరేటింగ్ స్టేషన్ లో
may not be 11, we have 25 kV generator also.
25 కూడా ఉందా సార్?
25 kV generator we have. Not necessary to design exact. Sorry, design the generator to develop only 11 kV.
సరే సరే అండి సార్, అంతేలేండి సార్. ఓకే సార్, థ్యాంక్ యూ.
Okay.
థ్యాంక్స్.
Yeah. Please raise your hands, else we can leave. Yeah, so I think nobody is having it out. Thank you.